Hello there, and welcome to Science for Sleep. I'm really glad you're here. Before we begin, take a moment to get comfortable. Maybe you're already lying down, maybe you're sitting somewhere quiet, or maybe this video is playing softly while you wind down after a long day. However you've arrived, you're in the right place. Science for Sleep is all about exploring big ideas in a calm and gentle way. No rush, no pressure to keep up with every detail. Just a slow journey through science, curiosity, and the universe, designed to help your mind relax while it learns something new. Tonight, we're going to explore a question that sounds simple at first. How big is TON 618 really? Now, if you've never heard of TON 618 before, that's completely okay. Even among astronomical objects, it's not something that usually comes up in everyday conversation. But once you learn about it, it quickly becomes one of those things that quietly reshapes the way you think about the universe. Because TON 618 isn't just large, it's not just extremely large. It's one of the largest black holes we have ever discovered. And when scientists try to describe its size, they often run into a strange problem. The numbers are so enormous that our brains struggle to attach any real meaning to them. We can write the numbers down, we can say them out loud, but actually imagining what they represent is another matter entirely. That's what we're going to explore together tonight. Not quickly. Not with complicated math or technical language. Instead, we'll move slowly, step by step, building a picture of just how enormous this object really is. But before we dive into the deep end of cosmic scale, let me ask you something simple. Where are you listening from tonight? Maybe you're at home, somewhere quiet. Maybe the lights are already off. Perhaps you're curled up under a blanket. Or maybe this video is playing softly on a phone beside your bed. Wherever you are in the world, it's interesting to remember that while you're listening to this, the universe above you is quietly continuing its vast and complicated story. Stars are forming, galaxies are drifting through space, and far beyond the reach of even the most powerful telescopes you could imagine looking through with your own eyes, TON 618 sits in the distant universe, doing what black holes do best: pulling, consuming, shaping the space around it. If you feel like sharing, you can always leave a comment about where you're listening from. It's always nice to see how far these quiet science journeys travel around the world. And if you find these kinds of slow explorations soothing, you can also like the video and subscribe to the channel. That helps more people discover Science for Sleep, and it allows us to keep making calm science stories like this one. Alright, now that we're settled in, let's begin with a very simple thought. Most of us have a basic idea of what a black hole is. Even if you've never studied astronomy, you've probably heard the phrase before. Black holes appear in movies, documentaries, and science books all the time. They've become one of the most famous objects in the universe. Usually they're described in a way that sounds a little mysterious. A place where gravity is so strong that nothing can escape, not even light. That description is actually quite accurate. A black hole forms when a large amount of matter is squeezed into an incredibly small region of space. When enough mass is packed together like that, gravity becomes extremely intense. If anything gets too close, it can no longer escape that gravitational pull. There's a boundary around a black hole called the event horizon. Once something crosses that boundary, there's no coming back. But here's something that might surprise you. Black holes are not all the same size. In fact, they come in a wide range of sizes, from relatively small ones formed by collapsing stars to enormous monsters sitting in the centres of galaxies. For example, if a very massive star runs out of fuel and collapses at the end of its life, it can leave behind a black hole that weighs maybe 10 times the mass of our Sun. That might already sound huge, and in a way it is. 10 suns worth of mass compressed into a region only a few dozen kilometres across is an astonishing thing. But compared to the giants of the universe, those stellar black holes are actually quite modest. At the centre of most galaxies, including our own Milky Way, scientists have found something much larger. These are called supermassive black holes. The one at the centre of our galaxy is known as Sagittarius A star. Its mass is about 4 million times the mass of the Sun. That number alone is already difficult to picture. 4 million suns. And yet, even that enormous object turns out to be relatively small compared to TON 618, because TON 618 belongs to an even more extreme category. It's what astronomers sometimes call an ultra-massive black hole, and its mass is so large that when scientists first calculated it, the results seemed almost unbelievable. TON 618 is estimated to contain around 66 billion times the mass of our Sun. 66 billion. Just saying the number out loud feels a little strange. Our brains are very comfortable with numbers like 10 or 100 or even 1,000. But once we move into billions, the scale becomes slippery. A billion seconds, for example, is more than 30 years. A billion minutes is over 1900 years. So when we say that TON 618 contains 66 billion suns worth of mass, we're stepping into a scale that stretches far beyond everyday experience. But here's where things become even more interesting. When people hear the word mass, they often imagine weight, something heavy, something dense. However, the size of a black hole is not just about how heavy it is. It's also about how wide the event horizon becomes. And for a black hole with tens of billions of solar masses, that event horizon grows to a truly enormous size. Large enough, in fact, to swallow our entire solar system many times over. We'll explore that comparison later, because it turns out to be one of the easiest ways to visualize the scale. For now, just keep one idea in mind. TON 618 is not merely a little bigger than other black holes. It's operating on an entirely different level. To understand how scientists discovered something this large, we need to step back for a moment and think about how astronomers actually study objects that are incredibly far away. After all, no one has ever visited a black hole. We can't send a spacecraft to hover nearby and take pictures. Even the closest black holes are far beyond the reach of current technology. Instead, astronomers rely on light. Telescopes collect tiny amounts of light that have travelled across the universe for millions or even billions of years. By analysing that light carefully, scientists can learn a surprising amount about distant objects. They can measure how fast something is moving. They can estimate its temperature. They can even figure out how much mass might be present. TON 618 was discovered through this kind of careful observation. At first, it didn't appear as a black hole at all. What astronomers actually saw was something called a quasar. Quasars are among the brightest objects in the universe. They shine with incredible intensity, often outshining the entire galaxy that surrounds them. That brightness doesn't come from the black hole itself, because black holes don't emit light. Instead, it comes from the matter swirling around the black hole. Gas and dust falling toward a black hole don't drop straight in immediately. Instead, they spiral inward, forming a spinning structure called an accretion disk. As that material spirals closer and closer, it heats up dramatically. Temperatures in these disks can reach millions of degrees. At those temperatures, the gas begins to glow intensely, producing enormous amounts of radiation. That glowing disk is what astronomers see from across the universe, and in the case of TON 618, the quasar it produces is unbelievably bright. So bright that it can be detected from billions of light years away. When astronomers studied the light coming from this distant quasar, they noticed something unusual. The gas around it was moving extremely fast, far faster than what would normally be expected. The only way to explain those speeds was the presence of an extraordinarily massive black hole. By analysing the motion of the gas and the brightness of the quasar, scientists were able to estimate the mass of the object at its centre. That's how they arrived at the astonishing figure of around 66 billion solar masses. Even today, TON 618 remains one of the most massive black holes we know about, and that raises a very natural question. If it's so massive, how big is it physically? How wide is the region where its gravity becomes impossible to escape? In other words, what would the event horizon actually look like if we could see it? Answering that question requires us to think carefully about scale. Because space, as it turns out, is very good at making even enormous things seem small. For example, our Sun feels huge when we think about it here on Earth. It's more than 100 times wider than our planet, and it contains more than 99% of the mass in the entire solar system. Yet when astronomers compare the Sun to other stars, it turns out to be fairly ordinary. And when we compare stars to black holes, the scale shifts again. TON 618 sits at the extreme end of that scale. Its event horizon stretches across a region of space so wide that if it replaced the Sun at the centre of our solar system, the boundary of no return would extend far beyond the orbits of many planets. But before we get into those comparisons in detail, it helps to take a moment to consider something else. Our brains are not naturally designed to understand cosmic distances. We evolved to think about things like walking distances, mountains, rivers, and maybe the size of cities. Even the scale of Earth itself can be difficult to fully appreciate. Once we start talking about objects that span billions of kilometers or masses that exceed billions of suns, we're entering a realm where intuition becomes unreliable. That's why astronomers often rely on comparisons. They take something familiar, like our solar system, and place it next to something unfamiliar, like TON 618. By stacking those comparisons carefully, they slowly build a picture that our minds can begin to grasp. And step by step we'll begin to answer the question that brought us here tonight. Just how big is TON 618 really? Somewhere above you right now, the night sky is quietly stretching in every direction. You might not be looking at it at this exact moment. Perhaps the curtains are closed, or the lights are off, and you're already resting. Maybe the sky outside is cloudy, or maybe it's glowing softly with the light of a city that never completely sleeps. But whether we see it or not, the sky is always there, a vast ceiling of space that surrounds our small planet on all sides. If you've ever stepped outside on a clear night far away from city lights, you probably remember that feeling. The first thing many people notice is how many stars there are. Not just a handful scattered across the sky, but thousands of faint points of light quietly shining from enormous distances away. At first they all look roughly the same. Tiny dots, some brighter than others, some dimmer, but still just points of light against the darkness. And yet each one of those lights is something enormous. Most of them are stars far larger than our Sun. Some belong to distant galaxies containing hundreds of billions of stars. Others are objects so energetic that they outshine entire galaxies by themselves. The strange thing about the night sky is that it hides its scale very well. Everything appears small. Everything appears calm and distant. Even the largest structures in the universe shrink down to tiny specks when we look at them from here on Earth. This creates a kind of illusion. When we glance upward, the universe doesn't look particularly large. It looks peaceful, quiet, manageable even. But that impression fades very quickly once we begin asking a simple question. How big are the things we're actually looking at? To answer that question, astronomers have had to build an entirely new way of thinking about size and distance. Because the scales involved in space are so large that ordinary units like kilometers or miles stop being very helpful. Let's start with something familiar. The distance between Earth and the Moon is about 384,000 kilometers. That already feels quite large by everyday standards. Driving that far would take several days without stopping. Flying that distance in an airplane would take many hours. Yet in astronomical terms, the Moon is practically right next door. Light from the Moon reaches Earth in just over 1 second. Now compare that to the distance between Earth and the Sun. Our planet orbits the Sun at an average distance of about 150 million kilometers. That number is so large that astronomers often shorten it into a special unit called an astronomical unit, or AU. 1 AU simply means the average distance between Earth and the Sun. Even with that enormous distance, sunlight still reaches us fairly quickly. It takes about 8 minutes for light to travel from the Sun to Earth. So far, the scale still feels somewhat understandable. The Moon is 1 second away, the Sun is 8 minutes away. But once we move beyond our solar system, the numbers begin to grow rapidly. The nearest star system to Earth is Alpha Centauri. Its light takes more than 4 years to reach us. That means the light we see from that star tonight actually left it 4 years ago. Because of distances like this, astronomers use another unit called the light year. A light year is simply the distance light travels in 1 year. Since light moves at about 300,000 kilometers per second, it covers an enormous amount of distance in that time. 1 light year equals about 9.46 trillion kilometers. Already our minds are being pushed into unfamiliar territory. Trillions, numbers that stretch far beyond everyday experience, but the scale keeps expanding. Our entire Milky Way galaxy is about 100,000 light years across. Inside it are hundreds of billions of stars, along with clouds of gas, dust, planets, and many other strange objects. And at the centre of this galaxy sits a supermassive black hole called Sagittarius A star. Earlier, we mentioned that this black hole contains around 4 million times the mass of our Sun. That might sound enormous, and it truly is. But compared to the giants of the universe, Sagittarius A is actually quite modest. TON 618, the object we're slowly working our way toward tonight, is far beyond that scale. But before we return to it, let's pause and think about something interesting. When you look up at the night sky, the stars appear scattered across a flat surface, almost like small lights on a dark ceiling. Your eyes can't easily detect how far away they really are. Some stars that appear close together in the sky are actually separated by hundreds or thousands of light years in space. Others may appear faint not because they are small, but because they are unimaginably far away. This is one of the reasons astronomy is such a patient science. Understanding the true scale of the universe requires careful measurement, observation, and a willingness to rethink our assumptions. For thousands of years, humans believed that Earth was at the centre of everything. The sun, moon, and stars seemed to circle around us each day. From the perspective of someone standing on the ground, that explanation made perfect sense. It wasn't until astronomers began studying planetary motion in more detail that the truth slowly emerged. Earth is not the centre of the universe. It's not even the centre of our solar system. And our solar system itself is just one small region inside a galaxy containing hundreds of billions of stars. Once that realization settled in, scientists began to ask deeper questions. If our galaxy is so large, how many other galaxies are out there? The answer, it turns out, is a staggering one. Modern observations suggest that the observable universe contains hundreds of billions of galaxies. Each galaxy may contain hundreds of billions of stars. That means the total number of stars in the observable universe could easily exceed the number of grains of sand on all the beaches of Earth. And among those countless stars and galaxies, black holes appear to be surprisingly common. Some are relatively small, formed when massive stars collapse at the end of their lives. Others are much larger, sitting quietly at the centres of galaxies and influencing the motion of billions of surrounding stars. But every once in a while, astronomers discover something that pushes the limits of what they expected to find. Objects that seem almost too large, almost too energetic. TON 618 is one of those discoveries. It exists at a distance of more than 10 billion light-years from Earth. That means the light we observe from it tonight actually began its journey across space when the universe was far younger than it is today. Back then, galaxies were still forming, stars were still being assembled from clouds of gas, and somehow, in that early cosmic environment, a black hole began growing into one of the largest objects of its kind that we've ever measured. But to appreciate just how extraordinary that growth is, we need to think carefully about scale once again. Because black holes behave differently from most objects we encounter in everyday life. If you double the mass of a rock, its size does not double in any dramatic way. If you double the mass of a planet, its diameter may grow slightly, but not enormously. Black holes follow a much more direct relationship between mass and size. As their mass increases, the radius of their event horizon increases in a predictable way. In other words, a heavier black hole is also physically larger. That means when we say TON 618 contains tens of billions of solar masses, we're not just talking about weight. We're also talking about an event horizon that stretches across a vast region of space, a boundary where gravity becomes so strong that even light cannot escape. This boundary defines the true size of a black hole, and in the case of TON 618, that size becomes almost difficult to comprehend. Imagine drawing a circle around an object where crossing that circle means there is no possible path back out again. No rocket could escape, no beam of light could return. Everything that crosses that boundary becomes permanently trapped. For a small stellar black hole, that circle might be only a few dozen kilometers across. For the black hole at the center of our galaxy, it spans tens of millions of kilometers. For TON 618, however, the circle grows to a scale that begins to compete with the dimensions of entire planetary systems. Trying to picture something like that can feel almost surreal. Our solar system itself is already huge. The orbit of Earth around the Sun covers nearly 1 billion kilometers each year. Even the orbit of Neptune, the outermost major planet, lies billions of kilometers from the Sun, and yet TON 618's event horizon would stretch across a region large enough to swallow a significant portion of that space. We'll explore those comparisons carefully as we move forward, because they help translate abstract numbers into something more tangible. But the night sky gives us another clue about scale that's worth considering. Every point of light we see represents a moment in the past. Because light takes time to travel, looking deeper into space also means looking further back in time. The moon appears as it was 1 second ago. The sun appears as it was 8 minutes ago. The nearest stars appear as they were years ago. Distant galaxies appear as they were millions or billions of years ago. TON 618 belongs to this distant past. When its light began travelling toward Earth, our planet was already billions of years old, but human civilization had not yet begun. In fact, complex life on land was still evolving. Dinosaurs had long since disappeared, and mammals were gradually spreading across the continents. Over the billions of years that followed, life on Earth changed dramatically. Continents drifted. Ice ages came and went. Eventually humans began looking up at the sky and wondering what those distant lights might be. Now, with modern telescopes and careful analysis, we can detect objects like TON 618, even though they exist unimaginably far away. That ability to measure and understand such distant things is one of the most remarkable achievements of science, but it also leads us back to the question that quietly sits at the center of tonight's exploration. If TON 618 contains tens of billions of solar masses, if it powers one of the brightest quasars in the universe, if it sits billions of light years away in a young galaxy, then just how large must its event horizon actually be? When people first hear the name TON 618, it doesn't immediately sound like anything familiar. It doesn't have a poetic name like Andromeda, or Orion, or even something descriptive like the Crab Nebula. Instead, it sounds a little more like a catalogue number, and that's exactly what it is. TON 618 is the name given to an object listed in a catalogue of astronomical observations. The TON part comes from the Tonantzintla Observatory in Mexico, where astronomers compiled a catalogue of unusual blue stellar objects many decades ago. These objects stood out because they appeared extremely bright and energetic when viewed through telescopes. At the time, no one knew that some of these strange points of light would later turn out to be among the most powerful objects in the entire universe. TON 618 was simply one entry in that catalogue. Just a small, distant point of light on photographic plates. But as telescopes improved and astronomers began studying it more carefully, something remarkable became clear. TON 618 wasn't a star at all. It was something far stranger. To understand what TON 618 really is, we need to step into a category of objects known as quasars. A quasar is one of the brightest things the universe can produce. In fact, a single quasar can shine more brightly than an entire galaxy, containing hundreds of billions of stars. That might sound almost impossible at first. After all, galaxies are enormous collections of stars, gas, dust, and dark matter. The idea that a single object could outshine an entire galaxy seems almost absurd. And yet quasars do exactly that. The reason is that the light we see from a quasar is not coming from a star. Instead, it comes from the environment surrounding a supermassive black hole. Now, black holes themselves don't emit light. They are called black holes precisely because they trap light rather than releasing it. But the material around a black hole can become extremely bright. Gas, dust, and other matter falling toward a black hole rarely plunge straight in. Instead, they form a rotating disk around it. This structure is called an accretion disk. You can imagine it somewhat like water spiraling down a drain, except on a vastly larger scale. As matter spirals inward, gravity squeezes it tightly and forces it to move faster and faster. Friction between particles heats the material to extraordinary temperatures, millions of degrees. At those temperatures, the gas begins to glow intensely, producing enormous amounts of radiation across many wavelengths of light. That glowing disk becomes visible across incredible distances. And when a black hole is actively feeding on large amounts of matter, the light from the surrounding disk can become so powerful that we see it as a quasar. TON 618 is one of those quasars. But it is not just any quasar. It is among the most luminous quasars ever observed. From Earth, the object appears as a faint point of light. Through a telescope, it doesn't look especially dramatic, but that faint dot represents something extraordinary. The light from TON 618 has travelled more than 10 billion years to reach us. That means when the light we see tonight left its source, the universe itself was much younger. Galaxies were still evolving. Stars were forming rapidly across the cosmos. The large-scale structures we see today were only beginning to take shape. Somewhere inside one of those distant galaxies, a black hole was growing at an astonishing rate, and that black hole is the engine powering the quasar we now call TON 618. When astronomers analysed the light coming from this object, they noticed something unusual about the gas surrounding it. The gas was moving extremely fast. In fact, it was moving so quickly that the only reasonable explanation was the presence of an incredibly massive black hole pulling on it. Using a technique called spectral analysis, scientists studied the light from the quasar in great detail. When gas moves rapidly, the light it emits becomes stretched or compressed in measurable ways. By analysing those changes, astronomers can estimate how fast the gas is orbiting the central object, and when they calculated those speeds, they arrived at a truly astonishing conclusion. The black hole at the centre of TON 618 contains tens of billions of times the mass of our Sun. Current estimates place it at roughly 66 billion solar masses. That number alone places it among the most massive black holes ever measured. To put that into context, let's briefly revisit the black hole at the centre of our own galaxy. Sagittarius A star contains about 4 million solar masses. That already sounds incredibly large, yet TON 618 outweighs it by more than 16,000 times. Another famous supermassive black hole sits in the centre of the giant galaxy Messier 87. This black hole, which was photographed by the Event Horizon Telescope in 2019, contains around 6.5 billion solar masses. That was once considered an extraordinary example of a massive black hole. But TON 618 is roughly 10 times more massive than that. Numbers like these begin to stretch our imagination in unusual ways. They're so large that they stop feeling meaningful. That's why astronomers often try to translate these values into physical size, because the mass of a black hole determines the size of its event horizon. The event horizon is the boundary around a black hole where escape becomes impossible. If you crossed that boundary, gravity would become so overwhelming that no amount of energy could carry you back out again. Even light cannot escape. For smaller black holes, this boundary can be surprisingly small. A stellar black hole containing 10 times the mass of the Sun might have an event horizon only about 60 kilometers across. That's smaller than many cities on Earth, yet the gravitational pull at that boundary would still be overwhelming. As the mass of a black hole increases, the event horizon grows proportionally. Double the mass, and the radius doubles. Increase the mass by 1,000 times, and the radius increases by 1,000 times as well. This simple relationship makes it possible to estimate the size of extremely massive black holes, like the one in TON 618. and when astronomers run those calculations, the results are astonishing. The event horizon of TON 618 is estimated to span hundreds of billions of kilometres. To give that number some perspective, consider the orbit of Neptune, the outermost major planet in our solar system. Neptune travels around the Sun at an average distance of about 4.5 billion kilometres. That's already a vast distance. Yet TON 618's event horizon is so enormous that it could easily swallow the entire region inside Neptune's orbit many times over. If the Sun were somehow replaced by this black hole, much of our solar system would lie well inside the point of no return. But TON 618's influence doesn't stop at its event horizon. Far beyond that boundary lies a vast region dominated by its gravity. Matter in this region can form enormous accretion disks stretching across distances comparable to entire planetary systems. Jets of energy can also erupt from the regions around the black hole, blasting radiation into intergalactic space. These energetic processes are what make quasars visible from such incredible distances. Without the glowing accretion disk surrounding TON 618, we might never have known it existed at all. The black hole itself remains invisible. What we see is the chaotic, glowing environment surrounding it, and even that environment lies billions of light years away. At such distances, individual details become impossible to observe directly. Instead, astronomers rely on careful measurements of light and motion to piece together what's happening. It's a bit like listening to distant thunder and using the sound to estimate the size of the storm. You can't see every detail of the clouds, but you can still learn a surprising amount about what's happening inside them. TON 618 represents one of the most extreme examples of this kind of cosmic detective work. A faint point of light in the night sky turned out to be powered by a black hole so massive that it challenges our understanding of how such objects grow. And that raises an interesting question. How does something like this become so large? Black holes usually grow in two main ways. They can swallow nearby gas and dust, gradually adding more mass over time. Or they can merge with other black holes when galaxies collide. Over billions of years, these processes can create very large black holes at the centres of galaxies. But reaching tens of billions of solar masses is still difficult to explain. TON 618 suggests that in the early universe, some black holes may have grown much faster than we once believed possible. Perhaps they formed from unusually massive seeds. Perhaps they consumed enormous amounts of matter in extremely dense young galaxies. Or perhaps there are growth mechanisms we still don't fully understand. Astronomers are still investigating these possibilities today. But for the purpose of our journey tonight, the important thing to remember is this. TON 618 is not simply a black hole. It is the central engine of a powerful quasar, a cosmic furnace powered by gravity, a region of space where enormous amounts of matter spiral inward, heating to incredible temperatures and releasing light that travels across billions of years of cosmic history. And at the centre of all that activity lies a gravitational boundary so vast that its true size is almost impossible to imagine at first. Try picturing something very simple for a moment. Imagine you are standing beside a familiar object, something you see often in everyday life, perhaps a house or a car parked along a quiet street. These are objects with sizes our minds understand easily. A car might be 4 or 5 meters long. A house might stretch 10 or 15 meters across. Even larger buildings, schools, offices, stadiums, still fall within a scale that feels manageable. Your brain has spent your entire life learning how to interpret sizes like these. If someone tells you that a building is twice as large as another building, you can picture that without much effort. If someone describes a mountain as being 3 times taller than another mountain, the idea still makes sense. The numbers remain connected to real experiences. But this comfortable sense of scale begins to weaken as soon as we start looking upward into space. Earlier we mentioned that TON 618 contains around 66 billion times the mass of our Sun. That number alone is already difficult to process, not because it is mathematically complicated, but because our intuition simply isn't built for numbers that large. And the moment we try to convert that mass into physical size, the difficulty becomes even more noticeable. Human intuition works best when it can compare things that belong to the same general category. For example, we understand the difference between a small lake and a large lake, or between a small town and a large city. Even when the difference is dramatic, the comparison still feels reasonable. Cosmic objects don't always behave that way. When black holes grow larger, their sizes increase in a very straightforward way. The relationship between mass and radius is almost perfectly proportional. This means that if one black hole is 10 times more massive than another, its event horizon will also be 10 times larger. That rule sounds simple enough, but when we apply it to something like TON 618, the consequences become extraordinary. Let's begin with a smaller example to build some intuition slowly. Suppose we take a black hole with the same mass as our Sun. If the Sun were somehow compressed into a black hole, the event horizon would only be about 3 kilometers across. That means all the mass of the Sun, over 300,000 times the mass of Earth, would be squeezed into a sphere about the size of a small town. That might already sound surprising. The Sun is enormous. Its diameter stretches roughly 1.4 million kilometers across. Yet as a black hole, it would shrink down to a sphere barely a few kilometers wide. Now, imagine a black hole 10 times the mass of the Sun. According to the same rule, its event horizon would grow to about 30 kilometers across. Still small by everyday standards. If you placed it somewhere on Earth, it would fit comfortably inside a large metropolitan area. But stellar black holes are only the smallest members of the black hole family. As astronomers began studying the centers of galaxies, they discovered something far more impressive. At the heart of many galaxies lies a supermassive black hole, containing millions or even billions of solar masses. Our own galaxy provides a useful example. Sagittarius A star, the black hole at the center of the Milky Way, contains about 4 million times the mass of the Sun. When we apply the same proportional rule, its event horizon expands to roughly 24 million kilometers across. That distance is already enormous. For comparison, the diameter of the Sun is about 1.4 million kilometers. This means the event horizon of Sagittarius A star is more than 17 times wider than the Sun itself. If it replaced the Sun in our solar system, the boundary where escape becomes impossible would extend nearly halfway to the orbit of Mercury. Already the numbers are beginning to stretch our imagination. But TON 618 sits in an entirely different category. Instead of millions of solar masses, it contains tens of billions. And because black hole size scales directly with mass, its event horizon expands accordingly. Astronomers estimate that the event horizon of TON 618 has a radius of roughly 195 billion kilometers. The diameter, stretching from one side of the event horizon to the other, would be nearly 390 billion kilometers. These numbers are so large that they almost stop feeling meaningful unless we compare them to something familiar. One useful comparison involves our own solar system. The orbit of Mercury lies about 58 million kilometers from the Sun. Venus travels at around 108 million kilometers. Earth orbits at about 150 million kilometers. Even the orbit of Neptune, the outermost major planet, lies roughly 4.5 billion kilometers from the Sun. When we place TON 618's event horizon beside those distances, something remarkable appears. The event horizon alone would extend far beyond the orbit of Neptune. In fact, it would reach several times farther than the outer planets. Imagine replacing the Sun with TON 618. Mercury, Venus, Earth and Mars would not simply orbit closer to the black hole, they would already lie deep inside the region where escape is impossible. The same would be true for Jupiter and Saturn. Even Neptune, which feels incredibly distant from the Sun, would be swallowed by the event horizon. Only the most distant icy objects of the outer solar system might remain outside that boundary. For many people, this is the moment when intuition begins to fail. The solar system already feels enormous to us. Space probes launched from Earth can take many years to reach the outer planets. The Voyager spacecraft, which left Earth in the 1970s, have been travelling for nearly half a century and are only now reaching the outer edge of the Sun's influence. Yet TON 618's event horizon alone would cover a region larger than that entire planetary neighbourhood, and that is just the boundary where escape becomes impossible. The gravitational influence of the black hole extends far beyond that point. Matter orbiting outside the event horizon can still move in stable paths, forming enormous disks of gas and dust. These disks can span distances far greater than the event horizon itself. In the case of powerful quasars like TON 618, the accretion disk becomes one of the brightest structures in the universe. Gas spiralling toward the black hole heats up dramatically as it loses energy and moves inward. Temperatures climb to millions of degrees, producing radiation across the electromagnetic spectrum. The result is a luminous beacon visible from billions of light years away. All of that activity occurs in a region dominated by the gravity of the central black hole, and the larger the black hole becomes, the larger that surrounding environment can grow. Another way to approach the scale of TON 618 is to compare it with other famous black holes astronomers have studied. In 2019, scientists captured the first image of a black hole's shadow using the Event Horizon Telescope. The object in that image was the black hole at the centre of the galaxy Messier 87. That black hole contains about 6.5 billion solar masses. At the time, it was considered one of the largest black holes ever measured. Yet TON 618 is roughly 10 times more massive than that. If you could somehow place both objects side by side, the event horizon of TON 618 would dwarf the one in Messier 87. But there is something even more interesting about extremely large black holes. Their event horizons are not only larger, they are also gentler in a certain sense. Near small black holes, the difference in gravity between your head and your feet would be enormous. This difference, called tidal force, would stretch objects dramatically as they approach the event horizon. The effect is sometimes described as spaghettification. For stellar black holes, this stretching would occur long before you reach the event horizon. But for ultramassive black holes like TON 618, the event horizon lies so far from the central singularity that tidal forces near the boundary are much weaker. In theory, an object crossing the event horizon of an ultramassive black hole might not notice anything unusual at that exact moment. There would be no visible surface, no sudden impact. Just a quiet transition into a region where escape becomes impossible. From the outside, however, the object would appear to slow down and fade away as it approached the event horizon. The light it emitted would become stretched and dimmer, eventually disappearing entirely. This strange behaviour comes from the way gravity affects time and light near extremely massive objects. It's one of the many reasons black holes remain such fascinating subjects of study. TON 618 takes all of these ideas and pushes them toward the extreme limits of what we currently observe in the universe. Its enormous mass produces a gravitational boundary larger than entire planetary systems. Its accretion disk releases enough energy to outshine the galaxy that hosts it, and its light has travelled across more than 10 billion years of cosmic history to reach our telescopes. Yet despite all of this scale, when astronomers look at TON 618 through a telescope, it still appears as a tiny point of light, a single faint speck in the sky. This contrast between appearance and reality is one of the most remarkable things about astronomy. The universe hides its largest structures behind distances so vast that they shrink down to almost nothing from our perspective. But with careful measurement and patient observation, scientists can slowly reveal what those distant specks truly represent. And once we start translating the numbers into familiar comparisons, solar systems, planetary orbits, and distances measured in billions of kilometres, the scale begins to come into focus. TON 618 is not just another large black hole. It represents a level of cosmic growth that challenges our understanding of how such objects form and evolve. At first glance, it might seem impossible to measure something that cannot be seen. If an object does not emit light, does not reflect light, and sits billions of light years away, the challenge begins to sound almost hopeless. Our everyday experience with measuring things usually depends on being able to see them clearly. You can measure the length of a table with a ruler, the height of a building with surveying tools, or the distance to a nearby hill with a laser rangefinder. All of those methods rely on one basic principle. You can observe the object directly. Black holes remove that possibility entirely. By their very nature, black holes trap light. Any light that crosses the event horizon cannot escape again. That means the defining boundary of a black hole, the event horizon itself, remains invisible to any telescope. So the question naturally arises, how do astronomers measure something that cannot be seen at all? The answer is surprisingly clever. Instead of trying to observe the black hole directly, scientists study everything around it. The space near a black hole is rarely empty. Gas, dust, and sometimes even entire stars can orbit nearby. These objects move under the influence of gravity, and their motion can reveal a great deal about the invisible mass at the centre. Gravity in this sense leaves fingerprints. When an object moves through space under the influence of gravity, its speed and direction depend on how strong that gravitational pull is. By carefully measuring those motions, astronomers can work backward and calculate the mass responsible for the movement. This method has been used many times in astronomy. In fact, it was used long before black holes were ever discovered. In the 19th century, astronomers noticed that the planet Uranus was not moving exactly the way they expected. Its orbit contained small irregularities that could not be explained by the gravitational influence of the known planets. Instead of dismissing the problem, scientists investigated further. They realized that the strange motion might be caused by another unseen planet, pulling on Uranus from farther out in the solar system. Using mathematics alone, they predicted where that hidden planet should be located. Soon afterward, telescopes were pointed toward the predicted location, and Neptune was discovered almost exactly where the calculation suggested it would be. This kind of reasoning, inferring the existence of an invisible object from its gravitational influence, became a powerful tool in astronomy. Black holes are discovered and measured using a similar approach. In the case of TON 618, astronomers did not see the black hole directly. What they observed instead was the extremely bright quasar produced by the matter swirling around it. As gas spirals toward the black hole, it forms the accretion disk we discussed earlier. This disk becomes incredibly hot, emitting enormous amounts of radiation across the electromagnetic spectrum. Telescopes can capture this radiation and spread it into a spectrum separating the different wavelengths of light, much like a prism separates sunlight into a rainbow. Inside that spectrum, astronomers look for specific patterns called emission lines. These lines come from atoms in the gas surrounding the black hole. When atoms absorb or release energy, they produce light at particular wavelengths. Hydrogen, helium, carbon, and many other elements each have their own recognizable signatures. But there is an important detail hidden within those lines. If the gas emitting the light is moving rapidly, the wavelengths shift slightly. This effect is called the Doppler shift. You might already be familiar with it in everyday life. When an ambulance passes by with its siren on, the pitch of the sound changes as it moves toward you, and then away from you. The sound waves are compressed as the ambulance approaches and stretched as it moves away. Light behaves in a similar way. When gas moves toward us, its light shifts slightly towards shorter wavelengths, appearing bluer. When it moves away, the light stretches toward longer wavelengths, appearing redder. By measuring these tiny shifts in the emission lines, astronomers can determine how fast the gas is moving. And near a massive black hole, the gas can move incredibly fast. In the case of TON 618, the gas within the quasar's broadline region, an area close to the black hole, was observed moving at thousands of kilometers per second. Such enormous speeds immediately suggest the presence of a powerful gravitational force. But astronomers don't stop there. Once the speed of the gas is known, the next step is to estimate how far that gas is from the black hole. This distance is more difficult to determine directly, but scientists use several clever techniques. One of them involves observing how the brightness of the quasar changes over time. Quasars are not perfectly steady sources of light. The brightness of the accretion disk can fluctuate as gas falls inward and energy is released. These fluctuations propagate outward through the surrounding gas clouds. By measuring the time delay between changes in the central brightness and changes in the emission lines produced by the surrounding gas, astronomers can estimate the distance between those regions. This method is called reverberation mapping. It works a bit like shouting inside a large canyon and listening for the echo. The delay between the shout and the echo reveals how far away the canyon walls are. In a similar way, the delay between changes in quasar brightness and changes in emission lines reveals how far the orbiting gas lies from the central black hole. Once both the speed of the gas and its distance from the centre are known, astronomers can apply the laws of gravity to estimate the mass of the object causing that motion. The calculation is similar to the one used to determine the mass of the Sun by studying the motion of planets. Planets orbit the Sun because of its gravitational pull. The faster a planet moves, or the closer it is to the Sun, the stronger that gravitational force must be. Gas orbiting near a black hole follows the same basic rules. For TON 618, these measurements revealed something extraordinary. The gas was moving so quickly and at distances so large that the mass required to produce that motion had to be tens of billions of times the mass of our Sun. No ordinary object could produce such an effect. Only an ultra-massive black hole could explain the observations. Once the mass is known, determining the size of the event horizon becomes relatively straightforward. Black holes obey a simple relationship known as the Schwarzschild radius. This radius defines the size of the event horizon for a non-rotating black hole. The formula itself is elegant. For every solar mass contained within a black hole, the radius of the event horizon increases by about 3 kilometers. This means a black hole with the mass of our Sun would have a radius of about 3 kilometers. A black hole with 10 solar masses would have a radius of about 30 kilometers. A black hole with 1 million solar masses would have a radius of roughly 3 million kilometers. The scaling continues smoothly as the mass grows larger. When we apply this relationship to TON 618, with its estimated 66 billion solar masses, the resulting event horizon becomes enormous. The radius reaches roughly 195 billion kilometers. That distance stretches far beyond the orbit of Neptune in our solar system. Yet even this calculation represents only the boundary where escape becomes impossible. The surrounding region dominated by the black hole's gravity extends much farther. Within that region, gas forms enormous rotating structures, and powerful jets of energy may erupt from the poles of the accretion disk. These jets can extend across distances larger than entire galaxies. All of this activity provides clues that astronomers can observe and analyze. Even though the black hole itself remains invisible, its presence shapes everything nearby. This idea, studying invisible objects through their influence, is one of the most powerful methods in modern astronomy. It allows scientists to explore parts of the universe that cannot be observed directly. Dark matter, for example, is detected through its gravitational effects on galaxies. Exoplanets are often discovered by observing the tiny wobbles they cause in the stars they orbit. Black holes follow the same pattern. We may never see the event horizon directly for objects as distant as TON 618, but we can still measure the mass and behaviour of the unseen object through the motion of the matter around it. In a way, the black hole reveals itself through the disturbances it creates. Gas accelerates, light shifts, energy radiates outward across billions of light years, and by carefully studying those signals, astronomers slowly assemble a picture of the hidden giant at the centre. TON 618 represents one of the most extreme examples of this process. From a faint speck of light in a distant galaxy, scientists have inferred the presence of a black hole so massive that its event horizon alone would dwarf our entire planetary system. Yet the story of how this object was first identified begins much earlier. long before its true size was understood. Decades ago, when astronomers first noticed this unusual point of light in the sky, they had no idea they were looking at one of the most massive black holes known. Long before astronomers understood what TON 618 really was, it appeared as something far less dramatic. To the observers who first recorded it, the object looked like a faint blue point of light on a photographic plate. It did not immediately announce itself as a giant black hole or a powerful quasar. Instead, it blended quietly among many other distant objects scattered across the sky. The story begins in the middle of the 20th century, during a period when astronomy was changing rapidly. For centuries, astronomers had relied on visual observation through telescopes. They would look through the eyepiece, carefully sketch what they saw, and record the positions of stars and planets. But by the early 1900s, photographic technology had transformed how the sky was studied. Instead of relying solely on human eyesight, astronomers could now capture large areas of the sky on photographic plates. These glass plates were coated with light-sensitive chemicals that reacted when exposed to starlight through a telescope. After the exposure, the plates were developed in a darkroom, revealing thousands of tiny points of light. Each of those points represented a distant object somewhere in the universe. Stars within our galaxy, clusters of stars, nebulae, galaxies far beyond the Milky Way, and occasionally something unusual. During the 1950s and 1960s, astronomers began paying close attention to certain objects that appeared particularly blue on these plates. Blue light in astronomy often signals extremely hot or energetic sources. Young stars, for example, can shine with a bluish colour because their surfaces are very hot. But some of the blue objects catalogued during this time behaved differently from ordinary stars. They appeared star-like in telescopes, meaning they looked like small points rather than extended structures like galaxies. Yet their light carried strange signatures when studied in detail. One catalogue that recorded many of these mysterious objects was compiled at the Tonantzintla Observatory in Mexico. Astronomers there were conducting a survey of blue stellar objects, points of light that appeared unusually blue compared to the surrounding stars. Each object in the catalogue received a simple label, TON followed by a number. TON 618 was one of those entries. At the time, it did not seem particularly special compared to many others. It was simply one more blue object recorded in the survey. But astronomy was entering a new era. As spectrographs improved, scientists began studying the light from distant objects in greater detail. A spectrograph spreads light into its component wavelengths, allowing astronomers to examine the unique patterns produced by different elements. When the spectrum of TON 618 was eventually analysed, the results were puzzling. Instead of the familiar patterns seen in ordinary stars, the light from this object showed broad emission lines, bright features produced by extremely energetic gas. Even more surprising was how wide those lines appeared. Broad emission lines indicate that the gas producing them is moving at extremely high speeds. The faster the gas moves, the more its light becomes spread out across different wavelengths. For TON 618, the speed suggested by those lines were enormous. Gas clouds appeared to be moving thousands of kilometers per second. Nothing in an ordinary star could produce such motion. Around the same time, astronomers were beginning to understand a new class of cosmic objects known as quasars. The term quasar originally stood for quasi-stellar radio source. Early radio telescopes had detected powerful radio emissions coming from objects that looked like stars in optical telescopes. At first, these discoveries confused scientists. How could something that looked like a star produce so much radio energy? The mystery began to unravel when astronomers studied the spectra of these objects and realized that they were not stars at all. They were incredibly distant galaxies whose central regions were producing enormous amounts of energy. The energy source behind these quasars turned out to be supermassive black holes feeding on surrounding matter. Once this idea became widely accepted, astronomers began re-examining many of the strange blue objects that had been catalogued earlier. TON 618 quickly attracted attention. Its spectrum showed the characteristic signs of a quasar, including extremely bright emission lines produced by hot gas near a powerful energy source. But there was another important clue hidden in the spectrum. The wavelengths of the light were shifted dramatically toward the red end of the spectrum. This effect, known as redshift, occurs because the universe is expanding. As light travels across vast cosmic distances, the expansion of space stretches the wavelengths of that light, making them appear redder than they originally were. The greater the redshift, the farther the object lies from Earth. When astronomers measured the redshift of TON 618, they discovered something remarkable. The object was incredibly distant, more than 10 billion light-years away. That means the light reaching Earth today began its journey long before our solar system had completed even half of its orbit around the Milky Way. In other words, the light we see now left TON 618, when the universe itself was much younger. At such enormous distances, an object must be extremely luminous to remain visible, and TON 618 was indeed extraordinarily bright. When astronomers calculated its luminosity, the total energy it emits, they realized that it was shining with the power of hundreds of trillions of suns. No single star could produce that much energy. The only explanation consistent with the observations was the presence of a massive black hole surrounded by a rapidly feeding accretion disk. Gas spiraling inward would heat up to millions of degrees, releasing tremendous amounts of radiation. This radiation would travel across billions of light years, eventually reaching telescopes on Earth. But the brightness of the quasar was only the beginning. As measurements improved, scientists began estimating the mass of the black hole responsible for this incredible energy. Using the techniques we discussed earlier, studying the motion of gas in the broadline region, and applying the laws of gravity, astronomers arrived at a stunning conclusion. The central black hole must contain tens of billions of solar masses. That estimate placed TON 618 among the most massive black holes ever discovered. And yet, despite its enormous scale, it remains invisible. Even the most powerful telescopes cannot resolve the structure of the black hole itself. From Earth, the entire system still appears as a single, distant point of light. But that faint point represents one of the most extreme environments in the universe. Gas racing at incredible speeds, temperatures rising to millions of degrees, radiation powerful enough to outshine the galaxy that hosts it. And at the centre of it all lies an event horizon so large that it would swallow our solar system many times over. The discovery of TON 618 illustrates something fascinating about astronomy. Sometimes the most extraordinary objects begin as quiet entries in a catalogue, a small mark on a photographic plate, a number assigned during a survey. Only later, through careful measurement and patient analysis, does the true nature of the object reveal itself. In this case, a faint blue point of light turned out to be the visible signature of one of the largest black holes known. Yet even now, TON 618 remains far beyond our direct reach. It sits billions of light-years away, deep in the distant universe, where the light we observe today began travelling toward us when galaxies were still forming. Despite that distance, its incredible brightness allows us to study it in surprising detail. Consider the amount of light produced by an entire galaxy for a moment. A galaxy like our own Milky Way contains hundreds of billions of stars. Each of those stars releases energy in the form of light and heat, steadily burning nuclear fuel deep in its core. Some stars are small and faint. Others are large and bright, radiating thousands or even millions of times more energy than our Sun. When all of those stars shine together, their combined glow creates the soft band of light stretching across the night sky that many people recognize as the Milky Way. From our position inside the galaxy, that glow can appear as a gentle river of starlight crossing the darkness. Yet if you were far outside the Milky Way and looking back toward it, the galaxy would appear as a luminous spiral island in space, filled with billions upon billions of shining suns. That amount of light is almost difficult to imagine, but here is the surprising part. The quasar surrounding TON 618 can outshine an entire galaxy like that. One single region near a black hole can release more energy than the combined output of hundreds of billions of stars. When astronomers first realized this, it seemed almost unbelievable. For a long time, galaxies themselves were thought to be the largest luminous structures in the universe. Their vast collections of stars, gas clouds, and glowing nebulae seemed unmatched in brightness and scale. The idea that a single compact object could rival or exceed that brightness felt counterintuitive, and yet that is exactly what quasars do. To understand why, it helps to think about the difference between how stars generate energy and how matter behaves near a black hole. Stars shine because of nuclear fusion. Inside the core of a star, hydrogen atoms are squeezed together under immense pressure and temperature. These atoms fuse into helium, releasing energy in the process. That energy slowly travels outward through the layers of the star until it finally escapes as light. Fusion is extremely powerful, compared with chemical reactions like burning wood or gasoline. But even fusion is not the most efficient way the universe can convert matter into energy. Black holes introduce a different process entirely. When gas falls toward a black hole, it does not immediately disappear beyond the event horizon. Instead, it forms a swirling structure called an accretion disk. Within this disk, gravity pulls the gas inward, while friction between particles causes the material to heat up dramatically. As the gas spirals closer to the black hole, it accelerates to incredible speeds. Some of the matter begins moving at a significant fraction of the speed of light. Under these extreme conditions, gravitational energy is converted into heat and radiation with remarkable efficiency. In fact, matter falling into an accretion disk around a black hole can convert up to about 10% of its mass into energy. That may not sound dramatic at first, but compared with nuclear fusion, it is astonishingly efficient. Fusion in stars converts less than 1% of the original mass into energy, so the process powering quasars can be more than 10 times as efficient as the process that powers stars. That difference explains why the regions around supermassive black holes can shine so brightly. When enormous amounts of gas are falling toward the black hole at the center of a quasar, the energy released can become staggering. The quasar surrounding TON 618 is one of the most extreme examples known. Astronomers estimate that it produces a luminosity equivalent to hundreds of trillions of suns. To put that into perspective, the entire Milky Way galaxy shines with a total luminosity roughly equal to about 100 billion suns. That means the quasar powered by TON 618 can be thousands of times brighter than our entire galaxy. Yet from Earth, this incredible energy appears as only a faint dot in the sky. Distance has a way of shrinking even the brightest objects into tiny points of light. TON 618 lies more than 10 billion light-years away. Over that immense journey, the light from the quasar spreads out in every direction across the expanding universe. By the time it reaches Earth, only a tiny fraction of that radiation enters our telescopes. Still, the quasar remains bright enough to be studied in remarkable detail. When astronomers analyze the spectrum of its light, they see the signatures of gas moving at extraordinary speeds. Clouds of material orbiting near the black hole reach velocities of several thousand kilometers per second. These motions broaden the emission lines in the spectrum, providing clues about the environment near the central object. The brightness of the quasar also reveals how much matter must be falling into the black hole. To maintain such a luminous output, the accretion disk must be continuously supplied with enormous quantities of gas. Vast streams of interstellar material likely flow toward the center of the host galaxy, feeding the black hole and sustaining the quasar's energy production. This feeding process may continue for millions of years. During that time, the quasar becomes one of the most dominant sources of radiation in its surrounding region of space. In fact, the energy released by quasars can influence the evolution of their host galaxies. The intense radiation and powerful winds produced near the black hole can push gas away from the galactic centre. These outflows may regulate how quickly new stars form, shaping the long-term development of the galaxy itself. In this way, a black hole that occupies only a tiny region at the centre of a galaxy can still affect structures spanning tens of thousands of light years. TON 618 demonstrates this relationship at a particularly extreme scale. Its enormous mass allows it to generate one of the most luminous quasars ever observed. The accretion disk surrounding the black hole glows with intense energy, while jets and winds may carry radiation far beyond the central region. Yet despite all this activity, the black hole itself remains hidden. No telescope can see the event horizon directly at such distances. Instead, astronomers observe the bright structures surrounding it, the glowing disk of gas, the fast-moving clouds producing emission lines, and the energetic radiation escaping into intergalactic space. All of these features combine to form what we recognise as a quasar. One interesting aspect of quasars is that they were far more common in the early universe than they are today. When we observe objects like TON 618, we are looking billions of years into the past. During that era, galaxies were younger and often contained large reservoirs of gas. Collisions between galaxies were also more frequent, funneling additional material toward their centres. These conditions provided abundant fuel for growing black holes. As gas poured into the central regions of galaxies, black holes could grow rapidly and power extremely bright quasars. Over time, however, many galaxies used up much of their available gas or expelled it through energetic outflows. As the fuel supply diminished, the quasars gradually faded. Today, most supermassive black holes appear relatively quiet. The black hole at the centre of the Milky Way, for example, is currently inactive compared with powerful quasars. Although it occasionally consumes small amounts of gas or dust, it does not produce the kind of intense radiation seen in objects like TON 618. This difference highlights an interesting phase in the life of galaxies. There may be periods when the central black hole becomes extremely active, shining as a quasar for millions of years. Later the activity subsides, and the galaxy settles into a quieter state. TON 618 represents one of those active phases at an extraordinary level of brightness. Because the quasar is so luminous, it can be detected even across enormous cosmic distances. Telescopes on Earth capture its light after a journey lasting more than 10 billion years. In a sense, observing TON 618 allows astronomers to look back into an earlier chapter of the universe. At that time, black holes were growing rapidly, and quasars illuminated the young cosmos with intense radiation. The light from TON 618 has been travelling through expanding space for most of the universe's history, before finally reaching our instruments. And all of that light originates from a region surrounding a black hole, whose true boundary, the event horizon, is still hidden from view. The brightness of the quasar helps us detect the object, but it does not reveal the exact size of the black hole itself. Imagine a boundary in space that cannot be crossed in reverse, not because there is a wall or a solid surface, but because the laws of physics themselves prevent anything from returning once that boundary is passed. No spacecraft could escape, no signal could travel back outward. Even light, which normally moves faster than anything else in the universe, would fail to break free. That boundary is what astronomers call the event horizon. It marks the point where gravity becomes so strong that every possible path leads inward. Outside the event horizon, objects can still move freely through space. They may orbit the black hole, drift away, or even escape entirely if they travel fast enough. But once the event horizon is crossed, every future direction points deeper toward the centre. For many people, the phrase black hole brings to mind an image of something like a cosmic vacuum cleaner, violently pulling everything inward from great distances. The reality is more subtle. A black hole behaves much like any other massive object when you're far away from it. Planets could orbit a black hole just as they orbit a star, provided they remained outside the event horizon. The true difference appears at that invisible boundary. The event horizon defines the size of a black hole, not the glowing accretion disk surrounding it, not the bright jets that may erupt from nearby gas. Those are dramatic features, but they are not the black hole itself. The black hole is defined by the region where escape becomes impossible. For smaller black holes, this boundary can be surprisingly compact. If our Sun were replaced by a black hole with the same mass, the event horizon would measure only about 3 kilometers in radius. That means the entire mass of the Sun, more than 300,000 Earths, would be compressed into a sphere smaller than many towns. From a distance, the gravitational pull would remain the same as the Sun's. Earth could continue orbiting exactly as it does now. The difference would appear only if something drifted too close to the event horizon. Then there would be no turning back. As the mass of a black hole increases, the radius of its event horizon grows proportionally. Every additional solar mass adds about 3 kilometers to the radius. This relationship, first described by the physicist Schwarzschild in 1916, allows astronomers to estimate the size of a black hole once its mass is known. The formula is simple. For every mass equal to our Sun, the event horizon expands outward by roughly 3 kilometers. When we apply that rule to extremely massive black holes, the size becomes astonishing. Consider the black hole at the center of our galaxy, Sagittarius A star. With a mass of about 4 million suns, its event horizon extends roughly 12 million kilometers in radius. That already sounds enormous. The entire diameter of the Sun is about 1.4 million kilometers, so the event horizon of Sagittarius A star is several times larger than the Sun itself. Yet on cosmic scales, that still counts as relatively modest compared with the giants found in some distant galaxies. TON 618 belongs to an entirely different category. Earlier we discussed how astronomers estimate that the black hole powering TON 618 contains around 66 billion solar masses. When the Schwarzschild relationship is applied to that mass, the size of the event horizon expands to a staggering distance. The radius reaches roughly 195 billion kilometers. That number can be difficult to interpret on its own, so astronomers often compare it with familiar structures in our solar system. For example, the orbit of Earth lies about 150 million kilometers from the Sun. The orbit of Jupiter stretches roughly 780 million kilometers outward. Neptune, the most distant major planet, travels around the Sun at an average distance of about 4.5 billion kilometers. Those distances already feel enormous. Spacecraft launched from Earth can take years to reach Jupiter, and more than a decade to reach the outer planets. Yet the event horizon of TON 618 would extend far beyond all of those orbits. Even Neptune would lie deep inside the boundary where escape becomes impossible. If this black hole somehow replaced the Sun at the center of our solar system, most of the planets would already be inside the event horizon. Only the farthest icy objects in the outermost regions might remain outside that invisible surface. This comparison reveals something important. The event horizon of TON 618 is not just large compared with planets or stars, it is large compared with the entire architecture of a planetary system. And that leads to a curious realization. For black holes of this scale, the boundary itself begins to feel less like a compact object and more like an enormous region of space. Imagine drifting slowly towards such a black hole from far away. At first, nothing unusual would appear. The black hole itself would remain invisible, hidden behind the darkness of its event horizon. The glowing accretion disk might be visible nearby, radiating enormous amounts of energy as gas spirals inward. But the event horizon would not look like a solid sphere floating in space. Instead, it would appear as a dark region where the background stars begin to distort. Gravity near the black hole bends the paths of light rays, creating dramatic gravitational lensing. Stars behind the black hole would appear warped and stretched into arcs of light. As you approached closer, time itself would begin to behave differently. According to the theory of general relativity developed by Albert Einstein, Strong gravitational fields slow the passage of time. Clocks near a black hole tick more slowly compared with clocks far away. An observer watching from a safe distance would see your spacecraft appear to slow down as it approached the event horizon. Light signals sent from the spacecraft would become stretched toward longer wavelengths, gradually fading until they disappeared entirely. From the perspective of that distant observer, the spacecraft would seem to freeze at the edge of the event horizon. But inside the spacecraft, the experience would feel different. You would continue moving forward normally. Your onboard clocks would tick as usual. Nothing special would happen at the exact moment you crossed the event horizon itself. That transition would be silent and invisible. Once inside, however, the path forward would lead inevitably toward the centre of the black hole. The remarkable thing about extremely large black holes like TON 618 is that the tidal forces near the event horizon can be relatively gentle. For small stellar black holes, tidal forces grow so strong near the event horizon that objects are stretched dramatically before they reach it. This stretching effect, sometimes called spaghettification, can tear apart anything approaching too closely. But for ultramassive black holes, the event horizon lies so far from the central singularity that the difference in gravity between one part of an object and another becomes much smaller at that boundary. In theory, a spacecraft crossing the event horizon of TON 618 might not experience extreme stretching immediately. The gravitational gradient at that enormous distance from the centre would be comparatively mild. Of course, travelling inside the black hole would still lead toward a region where gravity becomes overwhelming. But the size of the event horizon itself changes the nature of the journey. Instead of plunging instantly into destruction, an object might cross the boundary without noticing anything unusual at the exact moment it happened. This strange property highlights how scale transforms our understanding of black holes. For smaller black holes, the event horizon behaves like a sharply dangerous region, where tidal forces rapidly become extreme. For ultramassive ones, the boundary becomes enormous and surprisingly calm, at least locally. That calmness hides the deeper reality that no escape remains possible once the boundary is crossed. All paths through space-time begin to curve inward. For observers outside the black hole, the event horizon remains forever out of reach. Signals from beyond it can never return, meaning the interior remains hidden from the rest of the universe. Yet even without seeing inside, astronomers can still measure the size of that invisible boundary using the mass of the black hole, and in the case of TON 618, those measurements reveal something extraordinary. The event horizon alone spans a region wider than many entire planetary systems. Think about the layout of our solar system for a moment. Even though most diagrams show the planets neatly lined up close together, the real distances between them are enormous. Space inside our planetary neighbourhood is mostly empty. The sun sits at the centre, shining steadily, while the planets travel along wide circular paths that stretch billions of kilometres across. From Earth, those distances can feel abstract. The numbers are so large that they lose their meaning unless we imagine them step by step. Earth, for example, orbits the Sun at an average distance of about 150 million kilometres. Astronomers call this distance 1 astronomical unit, often shortened to 1 AU. It serves as a convenient measuring stick for distances within our solar system. Mercury, the closest planet to the Sun, travels at roughly 0.39 astronomical units. Venus moves along a path at about 0.72 astronomical units. Mars follows its orbit around 1.5 astronomical units from the Sun. These distances already feel large by everyday standards, but the outer planets push the scale much farther. Jupiter, the largest planet in the solar system, orbits at about 5.2 astronomical units. Saturn lies around 9.5 astronomical units from the Sun. Uranus travels at roughly 19 astronomical units, and Neptune, the outermost major planet, circles the Sun at about 30 astronomical units. Even at that distance, the Sun's gravity still dominates the motion of objects in the solar system. Beyond Neptune lies the Kuiper Belt, a wide region filled with icy bodies and dwarf planets. Farther still is the distant Oort cloud, a vast spherical halo of comets that may extend tens of thousands of astronomical units from the Sun. When we picture the solar system in this way, it becomes clear that our planetary neighbourhood is already incredibly large, and yet the event horizon of TON 618 would extend across a surprising portion of that space. Earlier we discussed how astronomers estimate the size of this black hole using the relationship between mass and radius, first described by Schwarzschild. With an estimated mass of about 66 billion suns, the resulting event horizon reaches roughly 195 billion kilometers in radius. That translates to about 1,300 astronomical units across in diameter. Numbers like these can still feel distant from everyday experience, so astronomers often compare them directly with the orbits of planets. Let's imagine placing TON 618 at the centre of our solar system, exactly where the Sun currently sits. At first glance, nothing would look very different from far away. The black hole itself would remain invisible, hidden behind its event horizon. The surrounding space would appear dark, except for any glowing material spiralling around it. But as we begin marking the positions of the planets relative to that event horizon, the scale becomes clear. Mercury, which orbits only 58 million kilometers from the Sun, would disappear instantly inside the boundary. Venus would also lie deep within the event horizon. Earth's orbit at 150 million kilometers would not even come close to the edge. Our planet would already be far inside the region where escape is impossible. Mars, which circles the Sun at about 228 million kilometers, would share the same fate. In fact, the event horizon of TON 618 would extend far beyond the entire inner solar system. Jupiter's orbit at roughly 780 million kilometers would also lie well within the boundary. Saturn, Uranus, and Neptune, planets we usually think of as extremely distant, would still be swallowed by the event horizon. To put this another way, the diameter of the event horizon is large enough to contain the orbits of every major planet in our solar system. Only the most distant regions of the Kuiper Belt would remain outside. Even then, the boundary would still stretch outward through a large portion of the space where icy dwarf planets and comets travel. For an observer watching from far beyond the solar system, the event horizon would appear as a vast invisible sphere engulfing nearly the entire planetary system. And yet, despite its enormous size, the black hole would not behave like a cosmic vacuum cleaner, pulling everything inward instantly. Gravity still follows the same rules. Objects outside the event horizon could orbit the black hole just as planets orbit the Sun today. If Earth somehow remained outside the boundary, perhaps placed far enough away, it could continue orbiting normally. The difference would appear only when an object drifted too close to the event horizon. Cross that invisible boundary, and no escape would be possible. This comparison reveals something remarkable about the scale of TON 618. Black holes are often imagined as compact objects, small regions where matter has been squeezed into extreme density. That description works well for stellar black holes created when massive stars collapse. But ultramassive black holes operate on a completely different scale. For TON 618, the event horizon alone covers a region wider than many planetary systems, and the event horizon is only the beginning. The gravitational influence of a black hole extends far beyond its boundary. Gas clouds orbiting nearby can form enormous accretion disks spanning distances much larger than the event horizon itself. In powerful quasars, these disks glow with incredible brightness as matter spirals inward and heats to millions of degrees. The accretion disk surrounding TON 618 likely extends across regions comparable to the size of the solar system, or even larger. Jets of high-energy particles may also erupt from the poles of the disk, blasting radiation across intergalactic space. All of this activity occurs within the gravitational reach of the central black hole. When astronomers observe such systems from Earth, they often cannot resolve individual structures because of the immense distance involved. Instead, they analyse the light coming from the quasar as a whole. From that light, they infer the speeds of gas clouds, the temperature of the accretion disk, and the mass of the black hole driving the entire process. Even though the black hole itself remains invisible, its influence reveals its presence. The comparison with our solar system also highlights something curious about scale in the universe. From our perspective here on Earth, the solar system feels enormous. The distance from the Sun to Neptune is more than 30 times the distance from Earth to the Sun. Spacecraft travelling at tens of thousands of kilometres per hour can take years to cross that distance. And yet TON 618's event horizon alone stretches far beyond that region. This kind of scale forces us to rethink what large really means. In everyday life, we measure things in meters or kilometres. In astronomy, we quickly move into millions, billions, and trillions of kilometres. Even then, the largest objects in the universe often exceed those measurements by enormous margins. TON 618 sits near the extreme end of that scale. Its event horizon could swallow the entire structure of our solar system with room to spare. And yet, despite this incredible size, it remains a single object. One black hole, one gravitational boundary, one engine powering a quasar bright enough to be seen across billions of light years. Somewhere deep in the centre of our own galaxy sits a black hole that astronomers have been studying for decades. It is hidden behind enormous clouds of gas and dust, far beyond the reach of any spacecraft we could send today. Even the most powerful telescopes cannot see it directly with ordinary light, yet its presence is unmistakable because the stars around it move in a very particular way. That object is known as Sagittarius A star. For many years, astronomers carefully tracked the motion of stars orbiting extremely close to this region. These stars whip around the invisible centre at incredible speeds, completing full orbits in only a few years. By measuring those orbits precisely, scientists were able to calculate how much mass must be concentrated in that tiny space. The answer turned out to be remarkable. Sagittarius A star contains about 4 million times the mass of our Sun. At first hearing, that number sounds enormous. 4 million suns compressed into a region smaller than the orbit of Mercury is already a dramatic example of how strange black holes can be. In fact, this discovery helped confirm that most large galaxies contain supermassive black holes at their centres. Our galaxy is not unusual in this respect. The Milky Way simply happens to be the one we can study most closely. Because Sagittarius A star is relatively nearby in cosmic terms, about 26,000 light-years away, astronomers have been able to observe the motion of individual stars around it. Those stars act almost like test particles tracing the shape of the gravitational field. Their paths reveal the mass hidden at the centre. One particular star, known as S2, travels on an extremely elongated orbit that carries it very close to the black hole every 16 years. During its closest approach, the star moves at thousands of kilometres per second. The gravity required to produce such motion can only come from a supermassive black hole. In 2020, the careful measurements of these stellar orbits earned the Nobel Prize in Physics for the scientists who led the research. But even though Sagittarius A star is impressive, it becomes something of a modest example once we compare it with the giant powering TON 618. Earlier we mentioned that TON 618 contains roughly 66 billion solar masses. When placed next to 4 million solar masses, the difference becomes staggering. TON 618 outweighs the black hole in our galaxy by more than 16,000 times. Numbers of that size can easily lose their meaning, unless we pause and translate them into something more concrete. One helpful way to think about the comparison is to consider the size of the event horizon. The event horizon of Sagittarius A star has a radius of about 12 million kilometres. That means the entire boundary of the black hole spans roughly 24 million kilometres across. Although that sounds enormous, it is actually smaller than the orbit of Mercury around the Sun. Mercury travels about 58 million kilometers from the Sun, so if Sagittarius A star replaced the Sun in our solar system, the event horizon would sit well inside Mercury's orbit. The planets could continue orbiting normally from a safe distance. Now imagine placing TON 618 in that same position. Instead of a boundary 24 million kilometers wide, the event horizon would stretch across nearly 390 billion kilometers. That distance reaches far beyond the orbit of Neptune and deep into the outer regions of the solar system. So the difference between the two black holes is not just large, it represents an entirely different scale. If Sagittarius A star were a small coin placed on a table, TON 618 would be more like an enormous stadium surrounding it. This comparison helps explain why astronomers sometimes refer to objects like TON 618 as ultra-massive black holes. They go far beyond the already impressive scale of typical supermassive black holes. Yet size is not the only difference between the two. Their environments also behave very differently. Sagittarius A star is currently quiet. Although small amounts of gas occasionally drift toward it, the black hole at the centre of the Milky Way is not actively consuming large quantities of matter. Because of that, it produces relatively little radiation compared with the bright quasars seen in distant galaxies. If we could observe Sagittarius A star from far away, it might appear almost invisible against the background of stars. TON 618, by contrast, is surrounded by one of the most luminous quasars ever observed. Gas falling toward the black hole forms an enormous accretion disk that glows intensely as it heats up. This disk radiates tremendous amounts of energy across the electromagnetic spectrum, including visible light, ultraviolet radiation, and X-rays. The energy output is so large that the quasar outshines the entire galaxy that hosts it. In other words, the black hole in our galaxy is currently resting, while the one inside TON 618 is actively feeding. This feeding process dramatically increases the brightness of the surrounding region. It also allows astronomers to study the system even though it lies billions of light years away. Without the quasar, TON 618 might have remained invisible to us. Another interesting difference involves how we detect each black hole. Sagittarius A star reveals itself through the motion of nearby stars. Because it is relatively close, telescopes can resolve individual stars orbiting around it. TON 618, however, is far too distant for that kind of detailed observation. Instead, astronomers analyze the light coming from the quasar and measure the motion of gas clouds near the black hole. These gas clouds produce broad emission lines in the spectrum, and their speeds allow scientists to estimate the mass of the invisible object at the center. Despite these differences, both black holes follow the same basic rules of gravity. Their behavior is described by the theory of general relativity developed by Albert Einstein. According to this theory, massive objects curve the fabric of spacetime around them. The stronger the mass, the deeper the curvature becomes. Black holes represent the most extreme example of this curvature. At the event horizon, the curvature becomes so strong that every possible path leads inward. This underlying principle remains the same whether the black hole contains a few times the mass of the Sun or tens of billions. What changes dramatically is the scale. Sagittarius A star bends space-time strongly within a region smaller than Mercury's orbit. TON 618 bends space-time across a region larger than our entire solar system. Another surprising consequence of this difference involves tidal forces. Near smaller black holes, tidal forces grow extremely strong as an object approaches the event horizon. The difference in gravity between the front and back of an object can stretch it dramatically. Near ultramassive black holes like TON 618, however, the event horizon lies so far from the central singularity that tidal forces at that boundary can be relatively mild. In theory, a spacecraft crossing the event horizon of TON 618 might not feel dramatic stretching immediately. This strange effect again shows how scale changes the nature of black holes. The larger the black hole becomes, the gentler the edge of the event horizon can appear locally, even though escape remains impossible once it is crossed. Looking at these two objects side by side, the quiet black hole in our own galaxy and the distant giant powering TON 618, offers a useful perspective on how varied black holes can be. Both obey the same physical laws, both warp spacetime around them, both possess an event horizon beyond which nothing returns. Yet their sizes, brightness, and environments can differ enormously. Sagittarius A star represents the kind of black hole found in many galaxies today. Massive, but relatively calm. TON 618 shows what can happen when a black hole grows to extraordinary mass while actively feeding on surrounding matter. It becomes one of the brightest objects in the universe. Galaxies often appear calm when viewed from a distance. Through a telescope, a galaxy might look like a graceful spiral of stars slowly turning through space. Billions of suns shine together, forming glowing arms that stretch across tens of thousands of light years. Clouds of gas drift between those stars, sometimes collapsing to form new generations of stellar systems. From far away, the entire structure can seem peaceful and orderly. Yet hidden deep inside many of these galaxies is something far more powerful. At their centres sits a black hole, not a small one formed from the collapse of a single star, but a massive gravitational anchor containing millions or billions of times the mass of the Sun. These central black holes are so common that astronomers now believe nearly every large galaxy hosts one. Our own galaxy is one example. The Milky Way contains a central black hole called Sagittarius A star. As we discussed earlier, that object holds about 4 million solar masses. It quietly influences the motion of stars in the innermost region of the galaxy, even though it occupies only a tiny portion of space compared with the galaxy itself. For a long time, astronomers were unsure whether this arrangement was unusual. Perhaps the Milky Way simply happened to contain a central black hole, while other galaxies did not. But as telescopes improved and more observations were made, a clear pattern began to emerge. Large galaxies almost always contain a supermassive black hole at their centre. Some of these black holes are relatively modest by cosmic standards, containing a few million solar masses. Others grow much larger, reaching billions of solar masses, and in extremely rare cases the central black hole can grow so large that it becomes one of the most massive single objects in the observable universe. The giant powering TON 618 belongs to this extreme category. To understand why galaxies contain these enormous objects, it helps to think about how galaxies themselves form and evolve. In the early universe, vast clouds of gas gradually collapsed under gravity to form the first galaxies. Inside those growing structures, stars began forming in enormous numbers. As the galaxies evolved, some of their gas sank toward the centre, pulled inward by gravity. At the same time, smaller galaxies frequently collided and merged with one another. When two galaxies merge, their central black holes can eventually drift toward the centre of the newly combined system. Over time, these black holes may merge as well, creating an even larger one. This process repeats over billions of years. Gas falls inward, stars orbit the centre, galaxies collide and merge. Black holes grow larger and larger as they absorb matter and combine with other black holes. Through these processes, the central regions of giant galaxies become home to extremely massive black holes. One of the most interesting discoveries in modern astronomy is that the mass of a galaxy's central black hole appears to be related to the mass of the galaxy itself. This relationship is known as the M-sigma relation. In simple terms, galaxies with larger central bulges tend to contain more massive black holes. The stars in those bulges move faster under the influence of the galaxy's gravity, and those stellar motions correlate closely with the mass of the central black hole. This suggests that galaxies and their central black holes grow together. Even though the black hole occupies only a tiny fraction of the galaxy's total volume, its influence can extend across vast distances. When a black hole actively consumes gas, the energy released in the surrounding accretion disk can heat or expel gas throughout the galaxy. This process may slow down the formation of new stars by pushing gas outward. Astronomers refer to this phenomenon as feedback. The black hole feeds on matter, releasing enormous energy in the process. That energy affects the surrounding galaxy, which in turn influences how much material continues falling toward the black hole. In this way, the galaxy and the black hole regulate each other's growth. For most galaxies today, this interaction has become relatively quiet. The central black holes remain in place, but they no longer consume large amounts of gas. Their surrounding regions have stabilized, and the galaxies evolve more slowly. But in the early universe, things were very different. Young galaxies contained much larger supplies of gas. Collisions between galaxies occurred more frequently. These conditions allowed central black holes to grow rapidly and power extremely bright quasars. TON 618 appears to be one of the most dramatic examples of such a system. Its central black hole has grown to tens of billions of solar masses, placing it among the largest black holes ever observed. Around it, enormous amounts of gas form a brilliant accretion disk that shines with incredible luminosity. This quasar releases so much energy that it can outshine the entire galaxy surrounding it. That fact alone reveals something remarkable. Normally, the light from billions of stars dominates the appearance of a galaxy. But in systems like TON 618, the central black hole becomes the brightest object by far. The galaxy becomes almost secondary to the quasar at its core. Even though the black hole itself remains invisible, its presence shapes the entire central region of the galaxy. Gas flows inward toward the accretion disk. Radiation pours outward into space. Jets of energetic particles may shoot away from the poles of the black hole, travelling across enormous distances. All of this activity occurs within a region only a tiny fraction of the galaxy's total size. The contrast between scale and influence is one of the most fascinating aspects of supermassive black holes. A galaxy might span 100,000 light-years across. The event horizon of its central black hole might measure only a few billion kilometers in diameter, and yet the energy released near that tiny boundary can influence the entire galaxy. TON 618 pushes this idea to the extreme. Its black hole is so massive that the event horizon alone would swallow our solar system if placed at the center. The surrounding accretion disk likely spans distances comparable to planetary systems or even larger. And all of this exists within a galaxy located billions of light-years away. Astronomers studying such objects often describe them as monsters at the centers of giant galaxies. Not because they're violent in a dramatic sense, but because their scale and power stretch far beyond anything found in ordinary stellar systems. Yet even these cosmic giants follow the same physical rules that govern smaller black holes. Gravity pulls matter inward. Energy is released as gas spirals toward the event horizon, and the surrounding environment reveals clues about the hidden mass at the center. In the case of TON 618, those clues reveal one of the largest gravitational engines ever discovered. Matter drifting through space usually behaves in a fairly predictable way. Gas clouds move slowly through galaxies, sometimes collapsing under gravity to form new stars. Dust grains float between those clouds, occasionally gathering into larger structures over millions of years. Even when gravity begins pulling material inward, the process often unfolds gradually. Stars form over long periods of time, and planetary systems assemble from rotating disks that evolve gently across vast stretches of time. The environment near a black hole changes that calm picture dramatically. As matter approaches a black hole, gravity begins to dominate every aspect of its motion. Gas that might have drifted peacefully through interstellar space suddenly accelerates. Paths that once curved gently now spiral inward with increasing speed. The closer the material moves toward the black hole, the stronger the gravitational pull becomes. Yet even here, the process is not as simple as matter falling straight into a dark opening. Space near a black hole is usually crowded with gas, dust, and radiation. Instead of plunging directly inward, most of that material begins to orbit. The result is a rotating structure known as an accretion disk. Inside this disk, matter behaves very differently from the gas clouds drifting through the rest of the galaxy. Each particle of gas is pulled inward by gravity while also moving sideways around the black hole. As these particles interact, they collide and rub against one another, creating friction. That friction converts gravitational energy into heat. The deeper the gas spirals into the disk, the hotter it becomes. Temperatures in the outer parts of an accretion disk might reach thousands of degrees. Closer to the center, the temperatures climb far higher, sometimes reaching millions of degrees. At those temperatures, the gas begins to glow intensely. Radiation pours outward across the electromagnetic spectrum from visible light to ultraviolet and even X-rays. This radiation is what allows astronomers to detect quasars across enormous cosmic distances. The quasar surrounding TON 618 shines so brightly because enormous amounts of matter are spiraling into the black hole's accretion disk. Every second, vast quantities of gas fall inward, releasing tremendous energy as they move closer to the event horizon. But the journey of that matter is not smooth. Inside the accretion disk, the gas moves at extraordinary speeds. Some of it travels at a significant fraction of the speed of light. At such velocities, even small collisions between particles can release enormous bursts of energy. Turbulence becomes common. Magnetic fields twist through the disk, stirring the gas and creating powerful currents of charged particles. These magnetic forces can fling some of the gas away from the disk entirely, launching it outward in high-speed winds. Not all the matter that approaches the black hole actually falls inside. Some of it is blown outward before reaching the event horizon. These outflows can carry huge amounts of energy into the surrounding galaxy, heating gas clouds and sometimes pushing material far away from the galactic center. At the same time, another dramatic phenomenon can occur near the poles of the black hole. In many active quasars, narrow beams of particles called relativistic jets erupt from the region close to the black hole. These jets travel outward along the black hole's rotational axis, shooting through space at speeds close to the speed of light. The exact mechanism that launches these jets is still an active area of research, but magnetic fields appear to play a crucial role. The spinning accretion disk and the rotation of the black hole itself twist magnetic field lines into tight coils. These magnetic structures can accelerate particles and channel them into narrow beams that escape far into intergalactic space. In some galaxies, these jets extend for hundreds of thousands of light years. For a distant observer, they appear as enormous streams of energy emerging from the center of the galaxy. All of these processes, heating, turbulence, radiation, and jets, occur in the environment surrounding the black hole. But eventually, some matter continues its inward spiral. As the gas approaches the event horizon, its speed increases dramatically. The gravitational pull becomes overwhelming, and the gas loses its ability to maintain stable orbits. At that point, the matter crosses the event horizon. From the outside, this transition is impossible to observe directly. The event horizon acts as a boundary where light itself cannot escape. Any signal produced beyond that point is trapped forever inside the black hole. However, the behavior of matter near the boundary reveals hints about what must be happening. Light emitted from gas close to the event horizon becomes stretched to longer wavelengths due to the intense gravitational field. This effect, known as gravitational redshift, makes the light appear dimmer and redder as it climbs away from the black hole. To a distant observer, matter falling toward the event horizon appears to slow down gradually. The closer it approaches the boundary, the slower it seems to move. Eventually, the light becomes so stretched that the infalling matter fades from view entirely. From the perspective of someone far away, it appears as if the matter never quite crosses the event horizon. Yet the matter itself experiences something different. From its own perspective, it continues falling inward without noticing any dramatic change at the exact moment the event horizon is crossed. This strange difference between viewpoints arises from the extreme effects of gravity on time and light. The theory describing these effects was developed by Albert Einstein in his theory of general relativity. According to that theory, massive objects warp the fabric of spacetime around them. Near a black hole, this curvature becomes so intense that all paths through spacetime eventually lead inward once the event horizon is crossed. Inside that boundary lies the region where gravity becomes truly overwhelming. The exact nature of what happens there remains one of the deepest mysteries in physics. At the very center of a black hole, general relativity predicts the existence of a singularity, a point where density becomes infinite and the known laws of physics break down. What truly happens at that location is still unknown. Physicists believe that a complete understanding may require a theory that combines general relativity with quantum mechanics. For the purposes of understanding TON 618, however, we do not need to explore the interior of the black hole itself. Everything we can observe occurs outside the event horizon. The accretion disk radiates enormous energy. Gas clouds orbit at incredible speeds. Jets may blast outward into the surrounding galaxy. And some of the matter continues its final inward journey toward the invisible boundary. Because TON 618 contains tens of billions of solar masses, these processes occur on an enormous scale. The accretion disk surrounding the black hole may extend across distances comparable to entire planetary systems. Gas clouds orbiting nearby move at thousands of kilometers per second, producing the broad emission lines astronomers observe in the quasar's spectrum. Despite the incredible violence of these environments, the edge of the event horizon itself may appear surprisingly calm. For ultramassive black holes, the tidal forces at that boundary are relatively gentle compared with smaller black holes. The immense size of the event horizon spreads the gravitational gradient over a much larger distance. This means that objects approaching the boundary might not experience dramatic stretching immediately. Instead, the final plunge into the black hole could occur quietly, at least at first. The true drama unfolds deeper inside, hidden forever from the outside universe. All of these behaviors, heating, radiation, jets, and the eventual inward fall of matter, combine to create the brilliant quasar we observe from Earth. That brightness tells astronomers that TON 618 is still actively feeding. Gas continues falling inward, allowing the black hole to grow larger over time. And this raises another fascinating question. How did a black hole manage to grow to such extraordinary size in the first place? Gas drifting through a galaxy does not usually fall straight into a black hole. Even though gravity pulls strongly toward the center, most matter in space carries some sideways motion. Clouds of gas rotate as galaxies spin, stars orbit around the galactic center, and dust grains move along curved paths shaped by gravity and past interactions. Because of this motion, when gas begins to move toward a black hole, it rarely plunges inward in a direct line. Instead, the material begins to circle around the black hole. As more and more gas accumulates in this region, it forms a flattened rotating structure known as an accretion disk. The disk resembles a vast cosmic whirlpool, with matter spiraling inward over time while gradually losing energy. Inside this disk, the conditions become extreme. Particles of gas crowd together, orbiting at enormous speeds while constantly colliding with one another. These collisions create friction, and that friction converts motion into heat. The deeper the gas moves into the disk, the faster it travels and the hotter it becomes. In ordinary environments, gas in interstellar space may remain only a few degrees above absolute zero. But in an accretion disk around a supermassive black hole, the temperature climbs dramatically. Outer regions of the disk may reach thousands of degrees. Closer to the center, the temperature can soar into the millions. At those temperatures, matter does not behave like familiar gases on Earth. Atoms become ionized, meaning their electrons are stripped away, leaving behind a hot plasma of charged particles. This plasma interacts strongly with magnetic fields, creating a turbulent environment filled with swirling currents of energy. The accretion disk becomes one of the brightest structures in the universe. Radiation pours outward across many wavelengths of light. Visible light, ultraviolet radiation, X-rays, and sometimes even gamma rays are released as the gas continues its slow inward spiral. This brilliant glow is what astronomers observe when they detect a quasar. The black hole itself remains invisible, but the surrounding disk shines intensely because of the enormous gravitational energy being released. The quasar associated with TON 618 is powered by exactly this process. Gas from the host galaxy falls toward the central black hole, forming an immense accretion disk. As the gas spirals inward, it heats up to extraordinary temperatures, producing the immense luminosity that allows astronomers to detect the quasar from billions of light years away. One remarkable feature of accretion disks is their efficiency. When matter falls toward a star, much of the gravitational energy is simply converted into heat inside the star's interior. But when matter falls into a black hole's accretion disk, a much larger fraction of the mass can be converted directly into radiation. This efficiency can reach around 10%. To understand how significant that is, it helps to compare it with nuclear fusion. Fusion inside stars converts only about 0.7% of the original mass into energy. Even though fusion powers the Sun and other stars for billions of years, the efficiency of black hole accretion is much higher. This means that a relatively small amount of matter falling into a black hole can produce enormous amounts of energy. The accretion disk becomes a kind of cosmic furnace, burning gravitational energy rather than nuclear fuel. Within that furnace, matter moves along complex paths shaped by gravity, friction, and magnetic forces. Gas in the outer regions of the disk orbits relatively slowly compared with gas closer to the center. But as the gas gradually loses energy through radiation, it drifts inward. Each step inward increases its orbital speed. Near the inner regions of the disk, matter can travel at a significant fraction of the speed of light. At such extreme velocities, the physics of the disk becomes incredibly complex. Magnetic fields twist through the plasma, generating turbulence that mixes material and redistributes angular momentum. This process allows some gas to move inward, while other gas is pushed outward. Without this transfer of angular momentum, the gas would simply remain in stable orbits and never reach the black hole. The disk therefore behaves like a constantly shifting system, with matter slowly migrating toward the event horizon over time. Some of that matter never reaches the black hole. Powerful winds can blow material away from the disk, carrying gas back into the surrounding galaxy. In some cases, these winds can become strong enough to affect the formation of stars in nearby regions by heating or dispersing gas clouds. The environment around an accretion disk can also produce another striking phenomenon. Jets of energetic particles sometimes emerge from the regions near the black hole's poles. These jets are narrow streams of plasma travelling outward at speeds close to the speed of light. They can extend across enormous distances, sometimes stretching tens of thousands of light years into intergalactic space. Although the exact mechanism that launches these jets is still being studied, astronomers believe that rotating magnetic fields play a crucial role. As the black hole spins, it drags space-time around with it in a process known as frame dragging. Magnetic fields embedded in the surrounding plasma can tap into this rotational energy, accelerating particles outward along the axis of rotation. The result is a pair of powerful jets emerging from the central region of the galaxy. In the case of extremely luminous quasars like TON 618, the accretion disk itself may extend across distances comparable to the size of our solar system. The outer parts of the disk glow with visible and ultraviolet light, while the inner regions produce X-rays as the gas reaches its highest temperatures. Because TON 618 lies billions of light years away, astronomers cannot directly image the disk itself. Instead, they study the light emitted from the quasar, and analyse the spectral signatures produced by gas in the disk and nearby regions. Those spectral lines reveal how fast the gas is moving, how hot it is, and how much material must be flowing toward the black hole. From these measurements, scientists estimate how quickly the black hole is growing. Even a black hole as massive as TON 618 can continue gaining mass as long as fresh gas keeps falling into the accretion disk. Over millions of years, this feeding process allows the black hole to increase its size. But the growth of such an enormous black hole raises an interesting puzzle. The universe itself is about 13.8 billion years old. TON 618 already contained tens of billions of solar masses when the light we see today began its journey toward Earth more than 10 billion years ago. That means the black hole must have grown extremely rapidly during the early history of the universe. Astronomers are still working to understand how this happened. Some theories suggest that the earliest black holes formed from the collapse of extremely massive stars, creating large seed black holes that could grow quickly by consuming gas. Other ideas propose that enormous clouds of gas in the early universe might have collapsed directly into black holes without forming stars first. Whatever the exact process, the accretion disk surrounding TON 618 played a crucial role in its growth. The disk acts as both a feeding mechanism and an energy source, allowing matter to spiral inward while releasing vast amounts of radiation into the universe. Without that cosmic furnace surrounding the black hole, the quasar would not shine so brightly, and astronomers might never have noticed this extraordinary object at all. Understanding how something becomes extremely large often begins with a simple question. Where did it start? Every object in the universe, whether it is a planet, a star, a galaxy, or a black hole, begins somewhere. Even the most enormous structures did not appear instantly at their full size. They grew over time, shaped by gravity, collisions, and the slow movement of matter across cosmic distances. This is also true for the black hole powering the quasar known as TON 618. Today, astronomers estimate that the mass of this object is around 66 billion times the mass of our Sun. That number places it among the largest black holes ever measured, but the universe did not begin with black holes that large. When the first stars and galaxies formed, black holes were much smaller. The puzzle astronomers face is understanding how something could grow from those smaller beginnings into an object as enormous as TON 618, especially within the relatively limited time available in the early universe. To explore that question, we have to step back and consider the environment of the young cosmos. The universe is currently about 13.8 billion years old. That sounds like an immense span of time, and in many ways it is. However, when astronomers observe TON 618, they are seeing it as it appeared more than 10 billion years ago. The light from the quasar began its journey toward Earth when the universe itself was only a few billion years old. That means the black hole had already reached its enormous mass relatively early in cosmic history. In other words, TON 618 did not have the full 13.8 billion years to grow. It had far less time than that. So how did it become so massive so quickly? Astronomers have developed several ideas to explain the growth of supermassive black holes. These ideas involve two key ingredients: the size of the original black hole and the rate at which it can gain new matter. Let's start with the first ingredient. Every supermassive black hole must begin with a smaller seed black hole. One possibility is that these seeds formed from the deaths of very massive stars. In the early universe, the first generation of stars, sometimes called population 3 stars, may have been much larger than most stars we see today. These early stars formed from pristine hydrogen and helium left over from the Big Bang. Without heavier elements to cool the gas clouds efficiently, the stars could grow to extraordinary sizes. Some of them may have contained hundreds of times the mass of the Sun. When such massive stars reached the end of their lives, they likely collapsed into black holes with tens or perhaps hundreds of solar masses. These would have served as the initial seeds. However, starting with a seed black hole of a few hundred solar masses still leaves a very long journey towards something as massive as TON 618. To grow into a black hole containing tens of billions of solar masses, the object would need to accumulate enormous amounts of matter. This leads us to the second ingredient, accretion. Black holes grow primarily by consuming gas, dust, and other material from their surroundings. As we discussed earlier, this material forms an accretion disk around the black hole and gradually spirals inward. The process releases enormous energy, which is why active black holes appear as quasars. But accretion cannot continue at an unlimited rate. There is a natural limit known as the Eddington limit. This limit arises because the radiation produced by the accretion disk pushes outward on the surrounding gas. If the black hole tries to consume matter too quickly, the outward pressure from radiation can blow that gas away before it falls inward. In other words, the black hole's own brightness can slow down its feeding process. At the Eddington limit, the outward pressure of radiation balances the inward pull of gravity. This balance determines the maximum rate at which a black hole can grow through steady accretion. Even at that maximum rate, the growth of a black hole takes time. If a black hole grows continuously at the Eddington limit, its mass doubles roughly every 45 million years. That may sound fast, but when starting from a small seed, reaching tens of billions of solar masses would still require many doubling periods. This is why TON 618 presents such an interesting puzzle. The black hole appears to have grown extremely quickly during the early universe. One possible explanation is that the original seed black hole was already much larger than the remnants of ordinary stars. Instead of forming from a stellar collapse, it might have formed through a process known as direct collapse. In this scenario, a massive cloud of gas collapses directly into a black hole without forming stars first. If the cloud is large enough, perhaps containing hundreds of thousands of solar masses, the resulting black hole could start out much larger than the seeds produced by stellar collapse. Beginning with a larger seed would make it easier to reach the enormous mass observed in TON 618. Another possibility involves galaxy mergers. In the early universe, galaxies frequently collided and merged with one another. When two galaxies merge, their central black holes can eventually spiral together and combine into a single, larger black hole. This process adds the masses of both black holes together. Over billions of years, repeated mergers could gradually build up extremely massive black holes at the centers of large galaxies. Gas flows triggered by these mergers could also feed the black hole more efficiently, allowing it to grow rapidly. TON 618 may have experienced several such growth phases. Large amounts of gas could have been funneled toward the center of its host galaxy, fueling the accretion disk and powering the quasar we observe today. Each episode of intense feeding would increase the mass of the black hole. Over time, these episodes could push the black hole into the ultramassive category. Another factor that may contribute to rapid growth is the density of gas in the early universe. Young galaxies often contained far more gas than many galaxies do today. That gas served as the raw material for star formation, but it could also feed central black holes. If a black hole sits in the middle of a dense supply of gas, it may be able to grow continuously for long periods of time. In such an environment, the black hole's mass could increase dramatically over a few 100 million years. The accretion disk surrounding TON 618 suggests that it is still actively feeding even today, at least in the distant past when the light we observe left the quasar. Gas continues to spiral inward, releasing enormous energy and allowing the black hole to gain additional mass. Over time, however, this feeding process may slow down. As the black hole grows larger and releases more energy, the radiation from the accretion disk can push surrounding gas away. Eventually, the supply of nearby gas may become depleted. When that happens, the quasar fades. The black hole remains in place at the center of its galaxy, but it enters a quieter phase where it consumes matter only occasionally. This may be the fate awaiting TON 618 in the distant future. The quasar may eventually dim as the surrounding gas supply decreases. The black hole will remain enormous, but much less active. Something similar has already happened in our own galaxy. The The black hole at the centre of the Milky Way is currently in a quiet state. Although it still occasionally consumes small amounts of gas, it no longer shines like a powerful quasar. Long ago, however, it may have experienced a much more active phase. Observations of large gamma-ray structures known as the Fermi bubbles suggest that Sagittarius A star may have released powerful jets in the distant past. If that interpretation is correct, then our own galaxy once hosted a much brighter central engine than we see today. TON 618 represents a galaxy caught during one of its most dramatic active phases. The black hole at its centre has grown to enormous size, and the surrounding accretion disk continues to radiate extraordinary energy. By studying such systems, astronomers hope to understand the processes that allow black holes to grow so large. Each observation adds another piece to the puzzle. How massive were the original seeds? How rapidly can accretion proceed under different conditions? How often do galaxies merge, and how much gas flows toward their centres during those events? These questions remain active areas of research. New telescopes and instruments continue to provide better data, allowing scientists to study quasars across vast distances and explore the history of black hole growth throughout the universe. And as those studies continue, objects like TON 618 remain among the most fascinating examples of how gravity, time, and matter combine to create some of the largest structures in the cosmos. Looking far away into space is also a way of looking backward in time. Light does not travel instantly. Even though it moves faster than anything else in the universe, it still requires time to cross the enormous distances between galaxies. Because of that, when astronomers observe very distant objects, they are not seeing them as they exist today. They are seeing them as they were when the light first began its journey. This simple idea has a remarkable consequence. The farther away we look, the younger the universe appears. Nearby stars show us the present state of our galaxy. More distant galaxies reveal what the cosmos looked like millions or billions of years ago, and the most distant quasars show us a universe that was still in its early stages of development. The quasar powered by TON 618 belongs to this distant past. The light reaching Earth today began travelling more than 10 billion years ago. At that time, the universe was only a fraction of its current age. Galaxies were still forming and evolving, and the first generations of stars had already lived and died. In other words, the enormous black hole we see in TON 618 had already grown to extraordinary size very early in cosmic history. This realization raises a fascinating question. How could such massive black holes appear so soon after the universe began? To answer that question, we need to imagine what the universe looked like during its early stages. After the Big Bang, the universe began expanding and cooling. In its earliest moments, it was filled with an extremely hot mixture of particles and radiation. Over time, as the temperature dropped, protons and electrons combined to form the first hydrogen atoms. For hundreds of millions of years, the universe contained mostly hydrogen and helium gas. There were no stars yet, no galaxies, just enormous clouds of gas slowly drifting through expanding space. Eventually, gravity began pulling some of that gas together. Small fluctuations in density grew stronger over time, allowing matter to gather into the first gravitational structures. Within these regions, the gas collapsed further, forming the first stars. Astronomers often refer to these early stars as population 3 stars. Unlike stars today, these first stars formed from pure hydrogen and helium. The heavier elements we see in modern stars, such as carbon, oxygen, and iron, did not yet exist. Those elements would be created later through nuclear reactions inside stars and during supernova explosions. Because the early gas lacked those heavier elements, it behaved differently during the star formation process. Modern gas clouds cool efficiently thanks to the presence of metals and dust. Cooling allows the gas to fragment into smaller pieces, producing many stars of moderate size. But in the early universe, the lack of heavy elements meant that gas clouds cooled less effectively. As a result, the collapsing gas often formed much larger stars. Some of these early stars may have been hundreds of times more massive than the Sun. Massive stars live short lives. They burn through their nuclear fuel quickly and end their lives in violent explosions known as supernovae. In some cases, the collapse of the stellar core produces a black hole. These black holes may have served as the first seeds for the supermassive black holes we observe today. A seed black hole formed from a massive early star might begin with a mass of tens or perhaps hundreds of suns. From there, it could begin growing by pulling in surrounding gas. But here is where the puzzle becomes more complicated. Even if a black hole continuously consumes matter, its growth rate is limited by the Eddington limit, the balance between the inward pull of gravity and the outward push of radiation produced by the accretion disk. This limit slows the feeding process. When astronomers calculate how long it would take a small seed black hole to grow into something as massive as Ton 618, the time required can appear uncomfortably long. In some cases, the growth time seems longer than the age of the universe at the time we observe the quasar. That suggests that something else may have happened during the early universe. One possibility is that some black holes began with much larger initial masses. Instead of forming from individual stars, these black holes might have formed through direct collapse. In this scenario, a massive cloud of gas collapses directly into a black hole, without first fragmenting into stars. If the gas cloud is large enough, the resulting black hole could begin with a mass of tens of thousands or even hundreds of thousands of solar masses. Starting with a larger seed would make it much easier to grow into an ultramassive black hole within a few billion years. Another factor that may have helped early black holes grow quickly is the abundance of gas in young galaxies. The early universe contained vast reservoirs of hydrogen gas that had not yet been converted into stars. This gas could flow toward the centers of galaxies, feeding the accretion disks around young black holes. Collisions between galaxies were also more common during this era. When galaxies merge, their gas clouds become disturbed and compressed. These disturbances can drive large amounts of gas toward the center of the newly combined galaxy. If a black hole already exists there, it can begin consuming this gas rapidly. The result may be an intense period of quasar activity. During such a phase, the black hole grows quickly, while releasing enormous energy into its surroundings. This may be exactly what happened in the case of Ton 618. The black hole may have experienced several episodes of rapid growth fueled by gas-rich mergers in the early universe. Each episode would add more mass to the black hole and increase the brightness of the surrounding quasar. Over time, these feeding events could produce the enormous mass we observe today. Astronomers continue to search for evidence of these early growth processes by studying quasars across different distances. Because light takes time to travel, observing very distant quasars allows scientists to examine black holes during different stages of cosmic history. Some quasars appear when the universe was only 1 billion years old. These early quasars already contain black holes with masses of billions of suns. Their existence suggests that black hole growth can proceed very rapidly under the right conditions. Modern telescopes continue to push these observations further. The James Webb Space Telescope has begun observing galaxies and quasars from extremely early periods of cosmic history. Its powerful infrared instruments allow astronomers to detect faint light from objects that formed not long after the first stars appeared. Each new observation helps scientists refine their understanding of how black holes and galaxies evolved together. The picture that emerges is one of a dynamic early universe. Gas flowed through young galaxies. Stars formed and exploded. Black holes grew rapidly at the centers of these systems. Over billions of years, these processes created the enormous structures we observe today. Ton 618 represents one of the most dramatic outcomes of that early cosmic evolution. Its black hole grew to a size rarely seen even in the modern universe. Yet despite its enormous mass, it still follows the same fundamental rules of gravity that govern every other black hole. Numbers that describe the universe often grow so large that they begin to feel almost abstract. When astronomers talk about billions of stars, trillions of kilometers, or black holes weighing tens of billions of suns, The human mind struggles to attach a clear picture to those values. It becomes easy to treat the numbers as symbols rather than something that represents real structures existing somewhere in space. Objects like TON 618 challenge us to confront those numbers more carefully. Because once astronomers began measuring the properties of this quasar and the enormous black hole powering it, a deeper question slowly emerged. Not just how large this particular black hole is, but whether there is a limit to how large black holes can become at all. At first glance, it might seem like black holes could grow without any upper boundary. Gravity pulls matter inward, and if enough gas and dust remain available, the black hole simply continues gaining mass. Galaxies collide, gas flows toward the centre, stars fall inward, and black holes merge with one another. Over billions of years, all of these processes could, in principle, allow a black hole to grow indefinitely. Yet when astronomers examine the universe carefully, they notice something interesting. Most supermassive black holes appear to fall within a certain range of masses. Many contain millions of solar masses. Some reach into the billions. A smaller number climb into the tens of billions. But beyond that, objects become increasingly rare. TON 618 sits near the upper edge of what astronomers currently observe. Its mass, estimated at around 66 billion times that of the Sun, places it among the largest known black holes in existence. That scale already stretches the imagination, but it also raises an important scientific question. Is this size close to the maximum that nature allows? To explore that possibility, astronomers consider the processes that allow black holes to grow. As we discussed earlier, the most important mechanism is accretion. Gas from the surrounding galaxy forms a rotating disk and gradually spirals inward, feeding the black hole. Each parcel of gas adds more mass to the central object, but accretion does not continue unchecked. When matter falls toward a black hole, the accretion disk becomes extremely hot. That heat produces enormous radiation, which pushes outward against incoming gas. Eventually, a balance forms between the inward pull of gravity and the outward pressure of radiation. This balance is known as the Eddington limit. When a black hole reaches the Eddington limit, the radiation from the accretion disk becomes strong enough to blow away some of the surrounding gas. The black hole can still grow, but its growth rate becomes regulated by this balance between gravity and radiation. This limit slows down the feeding process. Even if enormous amounts of gas are available, the black hole cannot consume all of it instantly. Instead, it grows gradually as matter continues spiraling inward. Over long periods of time, that gradual growth can still produce extremely massive black holes. But the Eddington limit acts like a natural speed limit, preventing runaway growth from happening too quickly. Another factor that influences the maximum size of black holes involves the galaxies that host them. Most supermassive black holes live at the centers of galaxies, and their growth depends on the supply of gas available in those environments. If the galaxy contains large amounts of gas, the black hole can continue feeding. But if the galaxy's gas becomes depleted, either because it forms new stars or because it is blown away by radiation and jets, the black hole's growth slows dramatically. Over time, the galaxy and its central black hole reach a kind of equilibrium. The black hole influences the galaxy through radiation and energetic outflows, while the galaxy controls the supply of matter available for accretion. This relationship explains why astronomers observe a strong correlation between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge. The two seem to grow together, shaping each other's evolution over billions of years. In this context, the enormous size of TON 618 suggests that its host galaxy must also be extremely large. Although the galaxy itself is difficult to observe because of the intense brightness of the quasar, it likely contains vast amounts of matter. That matter would have provided the fuel needed to build such an enormous black hole. Another growth mechanism also plays a role in determining the size of black holes. Galaxy mergers. When two galaxies collide, their central black holes may eventually spiral together and merge. This process adds their masses together, producing a single larger black hole. Over cosmic time, repeated mergers can gradually increase the size of central black holes in massive galaxies. TON 618 may represent the outcome of many such events. If its host galaxy merged with several other large galaxies during its history, each merger would have delivered additional gas and possibly another black hole to the centre. These events would accelerate the growth of the central object. But even mergers have limits. Galaxies do not collide endlessly. The number of large galaxies available for mergers decreases over time as the universe expands and galaxy clusters settle into stable structures. Eventually, the opportunities for massive black holes to merge become less frequent. When astronomers combine these factors, the Eddington limit, the supply of gas within galaxies, and the rate of galaxy mergers, they begin to see why ultramassive black holes like TON 618 are rare. Nature provides several pathways for black holes to grow, but each pathway includes mechanisms that slow the process down. These limits do not impose a strict maximum size. Instead, they make extremely large black holes increasingly unlikely. Even so, theoretical models suggest that black holes larger than TON 618 could exist. Some simulations indicate that black holes might reach masses of 100 billion solar masses under favourable conditions. Such objects would require exceptionally massive galaxies and long periods of sustained accretion. They would likely reside in the most massive galaxy clusters in the universe. Observationally, astronomers have identified a few candidates that may approach this range, although the measurements remain uncertain. TON 618 remains one of the clearest examples of an ultramassive black hole with a well-studied quasar. Its existence shows that the universe is capable of building black holes far larger than the one at the centre of our own galaxy, Sagittarius A star. Sagittarius A star contains about 4 million solar masses. Compared with the tens of billions contained in TON 618, that difference is almost difficult to grasp. The contrast highlights how diverse black holes can be across the universe. Some remain relatively small remnants of collapsed stars. Others grow into supermassive anchors at the centres of galaxies. And a rare few reach the ultramassive scale where their event horizons alone span regions larger than planetary systems. Studying objects like TON 618 allows astronomers to explore the extreme end of this range. By measuring their masses, analysing their spectra, and modelling the environments around them, scientists can test theories about how black holes grow and how galaxies evolve. These studies also help reveal the broader structure of the universe. The distribution of quasars across cosmic time tells us when black holes were most actively feeding. The masses of those black holes provide clues about the conditions in early galaxies. In a way, TON 618 acts as a kind of cosmic laboratory. It allows astronomers to study gravity operating at one of its most powerful scales. And as researchers continue discovering new quasars and measuring the masses of their central black holes, they move closer to answering a question that has fascinated scientists for decades. Is there truly a maximum size that a black hole can reach? Or could the universe still be hiding even larger giants somewhere in the depths of space? If the universe was capable of producing something this large, could it also produce something even larger? At first glance, the answer might seem simple. The universe is enormous. It contains hundreds of billions of galaxies, and each of those galaxies may host its own central black hole. Given such staggering numbers, it might feel reasonable to assume that somewhere out there, hidden among those galaxies, an even bigger black hole must exist. But when astronomers start examining the problem carefully, the question becomes much more interesting. Because while there is no simple law of physics that says a black hole cannot grow larger than TON 618, several factors begin to make such enormous objects increasingly difficult to form. Understanding those factors requires us to think again about how black holes grow in the first place. As we discussed earlier, the most common path toward becoming a supermassive black hole involves two main processes. The first is accretion, where gas and dust spiral inward through an accretion disk and gradually add mass to the black hole. The second is merging, where two black holes collide and combine into a larger one after their host galaxies merge. Both processes can contribute to the growth of extremely large black holes, yet both also have natural limits. Consider accretion first. When matter falls toward a black hole, it releases enormous amounts of energy as it heats up in the accretion disk. This energy escapes in the form of radiation, light, ultraviolet energy, and X-rays. But that radiation does not simply stream harmlessly into space. It also pushes outward on the surrounding gas. If the black hole begins feeding too quickly, the radiation becomes strong enough to push nearby gas away before it can fall inward. This balance between gravity pulling gas inward and radiation pushing it outward defines the Eddington limit. The Eddington limit does not completely stop growth, but it slows it down. Even if a galaxy contains a vast supply of gas, the black hole cannot consume all of it at once. Instead, it must grow gradually as material spirals inward at a rate that does not exceed this balance. Over millions or billions of years, that gradual feeding can still produce extremely massive black holes. But it becomes increasingly difficult to maintain the conditions needed for continuous growth. Eventually, the surrounding galaxy begins to change. As gas is consumed by the black hole or converted into new stars, the overall supply of available matter decreases. At the same time, the powerful radiation and jets produced by an active quasar can push gas away from the galactic center. In other words, the black hole's own activity can limit its future growth. This self-regulating process helps explain why most supermassive black holes fall within a particular range of masses. Even in the largest galaxies, the available fuel eventually becomes scarce. Merging black holes can also contribute to growth, but here too the opportunities are limited. Galaxies do merge, especially in the early universe when they were closer together. When two galaxies collide, their central black holes may eventually spiral toward each other and merge into a single, larger object. Each merger increases the mass of the resulting black hole. However, galaxy mergers are relatively rare events on cosmic timescales. After the universe expanded and galaxies settled into clusters and groups, the frequency of such collisions decreased. This means that although mergers can build larger black holes, they cannot continue indefinitely. The number of available partners gradually runs out. Even so, the universe has had billions of years to build enormous structures. When astronomers search the centers of giant galaxies, they occasionally find black holes that approach the scale of TON 618. Some estimates suggest that the most massive black holes may contain close to 100 billion solar masses. These objects are sometimes called ultramassive black holes. They appear to reside in the largest galaxies at the centers of galaxy clusters, regions where many galaxies have merged over long periods of time. In such environments, the conditions for growth may remain favorable for longer than in ordinary galaxies. Large reservoirs of gas can feed the central black hole, while repeated mergers contribute additional mass. Still, even in these extreme environments, black holes larger than about 100 billion solar masses appear to be rare. Part of the reason may involve the relationship between black holes and their host galaxies. Astronomers have discovered that the mass of a galaxy's central black hole tends to scale with the mass of the galaxy's central bulge. This relationship suggests that black holes and galaxies grow together. As the black hole becomes more massive, the energy it releases can influence the surrounding galaxy by heating gas and driving powerful outflows. Eventually, this feedback can reduce the amount of gas available for further growth. In a sense, the black hole regulates the evolution of its own host galaxy. If the black hole becomes too powerful, it may prevent the galaxy from delivering additional fuel to the center. TON 618 may represent one of the most extreme examples of this balance. The black hole grew enormously during an earlier phase when large amounts of gas were available. Today we observe it as a brilliant quasar shining across billions of light-years of space. But that bright phase may not last forever. Over time, the surrounding gas supply will likely diminish. The quasar will fade, leaving behind a giant black hole that continues influencing the motion of stars in its host galaxy. Astronomers sometimes imagine what a truly gigantic black hole might look like if it exceeded the scale of TON 618. The event horizon alone could stretch across distances larger than the entire planetary systems. The accretion disk surrounding it might span regions comparable to the size of a solar system or even larger. Jets of energy could extend tens of thousands of light years into intergalactic space. And yet, despite such enormous scale, the fundamental physics would remain the same. Gravity would curve spacetime around the black hole. Matter would spiral inward through an accretion disk. Radiation and jets would carry energy outward. The laws of general relativity would continue governing the structure of the event horizon. Even the largest black holes obey the same rules as the smallest ones. The difference lies only in scale. The existence of objects like TON 618 reminds astronomers that the universe is capable of building structures far larger than early scientists once imagined. For centuries, the Sun was considered a typical example of cosmic size. Later, astronomers discovered stars far larger than the Sun. Then they found galaxies containing hundreds of billions of stars. Now they observe black holes containing tens of billions of solar masses. Each discovery pushes our understanding of cosmic scale a little farther. And yet, even after discovering giants like TON 618, the universe may still hold surprises. The observable universe contains an enormous number of galaxies. Many of them lie far beyond the reach of current telescopes. In those distant regions, there may exist black holes that have grown under conditions we have not yet fully explored. Future observations may reveal objects even more massive than the ones we know today. New telescopes, improved instruments, and deeper surveys of the sky will continue expanding our view of the cosmos. Each discovery will help astronomers refine their understanding of how black holes grow and how galaxies evolve. And while TON 618 remains one of the largest black holes currently known, it may not represent the absolute limit. Somewhere out there, hidden among distant galaxies, the universe may still be building something even larger. Picture a spacecraft drifting through the quiet darkness between galaxies. The engines are silent now. The long acceleration phase finished years ago, and the craft is simply coasting through space. Outside the windows, the stars appear steady and distant, scattered across a deep black sky that stretches in every direction. Somewhere far ahead lies the distant galaxy that hosts the quasar powered by TON 618. At the beginning of the journey, there was nothing unusual to see. Even the most powerful telescopes show TON 618 as little more than a bright point of light. From billions of light years away, the entire galaxy collapses into a tiny speck against the darkness. The black hole itself cannot be seen at all. Only the radiation from the quasar reveals that something extraordinary exists there. As the spacecraft slowly approaches, that faint point begins to grow brighter. Over time, what once looked like a single star-like dot resolves into a distant galaxy. Billions of stars fill the sky ahead, forming a luminous structure slowly rotating through space. Spiral arms or elliptical clouds of starlight stretch across tens of thousands of light years. The galaxy itself would appear enormous long before the black hole becomes visible. From this distance, the central region of the galaxy would shine unusually brightly. That brightness comes from the quasar, where vast amounts of gas are spiraling inward toward the central black hole. Radiation pours outward from that region, carrying enormous energy across intergalactic space. As the spacecraft moves closer to the galaxy, the central glow grows more intense. The stars surrounding the galactic core become easier to distinguish. Their orbits curve around an invisible center where gravity dominates the motion of everything nearby. At the very heart of that motion lies the black hole itself, still invisible, still hidden behind its event horizon. The quasar surrounding it, however, becomes increasingly dramatic. Gas clouds swirl through the central region, forming an enormous accretion disk that shines with extraordinary brightness. The disk is not flat like a solid plate, but more like a glowing whirlpool of plasma circling around the black hole. Temperatures in the inner regions reach millions of degrees. Radiation emerges across many wavelengths: visible light, ultraviolet energy, and powerful X-rays. Approaching this region would require extraordinary shielding. The radiation environment near a quasar can be extremely intense. Any spacecraft venturing too close would need protection against the energetic particles streaming outward from the accretion disk and surrounding gas. But even from a safe distance, the view would be remarkable. The disk would appear as a brilliant ring of light encircling a dark central region. That darkness marks the location of the event horizon, the boundary where gravity becomes so strong that light cannot escape. For a black hole as massive as TON 618, the event horizon spans an astonishing distance. Earlier we discussed how its diameter stretches hundreds of billions of kilometers across. To put that into perspective, imagine placing the black hole at the center of our solar system. The event horizon would extend far beyond the orbit of Neptune. A spacecraft approaching the black hole would therefore encounter its gravitational influence long before reaching the event horizon itself. Even thousands of millions of kilometers away, the gravity of the black hole would already shape the motion of nearby gas and stars. Yet gravity behaves differently near such an enormous object. For smaller black holes, the tidal forces near the event horizon become extremely strong. The difference in gravity between the front and back of an object can stretch it dramatically as it approaches the boundary. This effect is often described as spaghettification, but TON 618 is so massive that its event horizon lies very far from the central singularity. Because of this enormous scale, the tidal forces at the event horizon would actually be relatively gentle compared with those around smaller black holes. A spacecraft crossing the event horizon of such a giant might not experience dramatic stretching immediately. Instead, the transition could feel surprisingly calm at first. Of course, from the perspective of a distant observer watching the spacecraft approach the event horizon, something very strange would appear to happen. As the spacecraft gets closer to the boundary, the light it emits becomes increasingly affected by gravity. According to the theory of general relativity developed by Albert Einstein, strong gravitational fields slow the passage of time relative to distant observers. This means that clocks near the black hole tick more slowly than clocks far away. To someone watching from a safe distance, the spacecraft would appear to slow down as it approaches the event horizon. Its signals would become stretched to longer wavelengths. The light would gradually redden and fade. Eventually, the spacecraft would appear almost frozen at the edge of the black hole, its image growing dimmer and dimmer until it disappeared entirely. Yet for the travellers aboard the spacecraft, the experience would feel very different. Inside the ship, time would continue passing normally. The crew would see the glowing accretion disk surrounding them, its light bending around the black hole due to gravitational lensing. Stars behind the black hole would appear warped into arcs and rings as their light curves around the intense gravitational field. This bending of light creates one of the most dramatic visual effects near a black hole. The black hole itself would appear as a dark sphere against the bright background of the disk and distant stars. The surrounding light would curve around it, forming a distorted halo. As the spacecraft crossed the event horizon, there would be no visible surface, no sudden impact, just a silent crossing into a region where escape becomes impossible. From that moment onward, every possible path through space-time would lead inward toward the center. The crew might continue observing the outside universe for a time, but signals they send outward would never escape the black hole's gravity. Eventually, the journey would carry them deeper toward the region where gravity becomes overwhelming. What lies at the center of a black hole remains one of the greatest mysteries in modern physics. General relativity predicts a singularity, a point where density becomes infinite and the known laws of physics break down. Many physicists believe that a deeper theory combining gravity with quantum mechanics will eventually reveal a more complete picture. For now, however, the interior of a black hole remains hidden behind the event horizon. No information from that region can reach the outside universe. Even so, imagining a journey toward a black hole like TON 618 helps us appreciate the incredible scale involved. The event horizon alone stretches across distances larger than planetary systems. The accretion disk surrounding it shines brighter than entire galaxies, and the gravitational field near the black hole warps space and time in ways that challenge our everyday understanding of reality. All of this exists in a distant galaxy whose light has travelled billions of years to reach us. From Earth, TON 618 appears as a small point of light in the sky, yet behind that faint glow lies one of the most powerful gravitational engines ever discovered. And thinking about such enormous objects inevitably leads us back to a quieter question. After exploring these immense scales and distant structures, what does all of this tell us about the universe we inhabit? Step outside on a calm evening and look up for a moment. The night sky rarely looks dramatic at first glance. A few bright stars may stand out. Perhaps a faint band of light stretches across the sky if you're far enough from city lights. Planets might appear as steady points that do not twinkle as much as the surrounding stars. For most people, the view feels peaceful and familiar. Nothing about that quiet scene suggests the enormous structures that exist beyond what the eye can easily see. And yet, hidden within that calm sky are objects whose sizes and energies stretch far beyond ordinary experience. Among them is the distant quasar powered by TON 618. When astronomers observe that object through powerful telescopes, they see a tiny point of light. From Earth, it does not appear large or unusual. Without careful analysis, it could easily be mistaken for a distant star. But that faint point represents one of the largest black holes currently known. Its event horizon alone stretches across a region larger than our entire solar system. Gas spiraling around it forms a glowing accretion disk releasing enormous energy. Jets of radiation may shoot outward across distances that rival the size of galaxies. All of this activity is taking place billions of light years away, and the light we observe today began its journey long before human civilization existed. When that light first left its source, Earth was already billions of years old, but life on our planet was still evolving toward the forms we recognize today. Continents were shifting slowly across the surface. Ancient ecosystems were changing. The earliest ancestors of modern animals were beginning to spread across land and sea. During that same era, the quasar around TON 618 was shining brightly in a distant galaxy. Its light started travelling across the expanding universe, passing through vast regions of space filled with other galaxies, stars, and dark matter. For billions of years, that light continued its journey. Eventually, a tiny fraction of those photons reached the region of space that would later become our solar system. Even then, they still had far to travel. Earth itself formed about 4.5 billion years ago. For much of that time, no creatures existed that could observe the sky in a scientific way. The light from TON 618 continued streaming through space while life slowly evolved on our planet. Only very recently, on cosmic timescales, did humans begin building instruments capable of detecting distant quasars. With telescopes and spectrographs, astronomers learned how to study the faint light arriving from remote galaxies. By analysing the spectrum of that light, they discovered the signatures of fast-moving gas near enormous black holes. That is how TON 618 was eventually recognised for what it truly is: not a star, not even a normal galaxy, but a quasar powered by one of the most massive black holes ever measured. The discovery of objects like this has gradually changed the way we understand the universe. For much of human history, the night sky appeared relatively simple. The stars seemed fixed in place, forming patterns that repeated night after night. Ancient observers used those patterns for navigation, storytelling, and calendars. The deeper structure of the cosmos remained hidden. Over the past century, that hidden structure has slowly been revealed. Astronomers learned that the stars belong to a vast galaxy known as the Milky Way. Later, they discovered that the Milky Way is only one of billions of galaxies scattered across the universe. Within many of those galaxies lie supermassive black holes. Some are quiet, like the one at the centre of our own galaxy, Sagittarius A star. Others shine brilliantly as quasars when large amounts of gas fall toward them. TON 618 represents one of the most extreme examples of that phenomenon. It reminds us that the universe contains structures operating on scales far larger than anything we encounter in everyday life. Black holes with masses of tens of billions of suns, accretion disks glowing brighter than entire galaxies, event horizons wide enough to swallow planetary systems. These ideas can feel almost surreal when we first hear them. But the remarkable thing is that they are not speculation or imagination. They are conclusions drawn from careful observation and measurement. Light travelling across billions of years carries information about the objects that produced it. By studying that light, astronomers can reconstruct the properties of distant quasars, estimate the masses of their central black holes, and trace the history of cosmic evolution. Every photon arriving at a telescope contains a small piece of that story. TON 618 is only one example among many discoveries that have reshaped our understanding of the cosmos, yet it holds a special place because of its extraordinary scale. It sits near the upper end of the black hole mass range currently known. Studying it helps astronomers explore the limits of how large black holes can become and how quickly they can grow. These investigations continue today. New telescopes are constantly expanding our ability to observe the distant universe. Instruments capable of detecting faint infrared light can peer deeper into cosmic history, revealing galaxies and quasars from earlier periods of time. Each new observation may uncover objects even more massive than the ones we know. Somewhere out there, beyond the reach of our current instruments, there may be black holes larger than TON 618. Or perhaps TON 618 already sits close to the natural limits imposed by the laws of physics and the evolution of galaxies. Astronomers are still working to answer that question, but even without knowing the final answer, the existence of TON 618 already tells us something important. The universe is capable of building structures on a scale far greater than our everyday intuition would suggest, and yet those enormous structures remain connected to the same physical laws that shape everything else. Gravity pulls matter together. Energy is released when matter falls into deeper gravitational wells. Time and space respond to mass and motion according to the rules described by general relativity. From the collapse of a star to the growth of a quasar billions of light years away, the same fundamental principles apply. As you look up at the night sky again, it is worth remembering how much complexity hides behind those small points of light. Some of the stars you see belong to our own galaxy. Others may be distant galaxies whose light has travelled millions of years to reach us. And far beyond what the naked eye can detect lie objects like TON 618, shining quietly across unimaginable distances. Their light continues travelling through space even now. Some of it may still be billions of years away from reaching the next telescope that will detect it. The universe does not rush. Its largest structures evolve slowly across immense stretches of time. Stars form, burn and fade. Galaxies drift through space and occasionally merge. Black holes grow, feed, and sometimes fall silent. Through careful observation, we have begun to understand a small part of that vast story. And tonight, by following the faint trail of light from one distant quasar, we've taken a quiet journey across billions of years and unimaginable distances, all the way from our small planet back to the silent sky above us.